Hello. It is time. Alright. I mean, I guess I already gave it away because, you know, title stream. Robot spider thing. So I'm just gonna go right into that. Well, actually, technically first what I'm supposed to do is this. I have my I need the max slope angle. So today, max slope angle, rid of that. If the, and I guess also, I probably need multiple collisions because, yeah, this probably is the case where I may need multiple collisions because I do still have a problem where if I walk into a wall, my new collision is on that wall and I can start sinking into the ground, essentially, which causes issues. So I'll start with max slope angle. If the first collision exceeds a, well, I guess, yeah, I'll just start with this. If the first collision exceeds a certain angle, consider to not be on ground. It should be that simple. And then I guess I need to also add this. Handle more than one collision. Pick the best angle, I guess. Pick the best floor angle as the primary collision. So I'm actually going to start with both of those. Maybe I should reconsider that. This second bit about the collision. let me see how it goes. I think the real issue is that when I have stuff colliding with shapes kind of intersecting too much, then it causes issues. Or not shapes intersecting. The same object having intersecting shapes can cause issues. Because I kind of detect the first collision and I detect like the nearest hit and then I don't detect any other hits. Which is technically not very, maybe that's not very good for I mean, I'll just look at this, right? So if I walk up into this, so really I just shouldn't be allowed to walk on that at all. I should stop any forward motion. I also think I'm thinking 60 degrees is about my limit. And then I'm thinking also didn't realize this drew a ray. That's good. The bounce I'm not really concerned about. Not really concerned about the bounce. I should probably try to fix it just by increasing the damping slightly, but here's a vertical wall I can walk into. Yeah. Oh. Oh, hang on, what? This is weird. If I do this and let myself fall, I'm like stuck here. Oh, or not. Oh, I think it's because my angle, I'm detecting my stable angle as the slope, and so I'm trying to move down the slope. And I have such a small velocity away from the slope that I kind of stick to it a little bit. That's what that was. All right, just max floor angle. I'm gonna start there. Let me look at this. Okay. Max slope angle, and then I can look at other stuff. Whoops. Export. Range. This will be given in degrees, but whenever I I think I'd actually like to just give it as the cosine theta of the angle. I'll have it... Ideally, I just pass in a value between 0 to 1. And I would have to compute that. But as far as like a setting, making that setting happen, I prefer to type in a specific angle. And then it's always kind of... It's difficult. Oh, wait a second. I can do radians as degrees. So I can display degrees, but I provide radians. That's at least a good step. So I'll say 0, and I'll just say 89 degrees is your limit. And I don't think you should be any more precise than that. So this will be radians as degrees. And that should give me like a suffix for degrees. And then I need a radians, degged red. For a good default, I'll just say 60 degrees. floor angle at which point the controller will be considered. I don't really think that. I'm sure the controller will not be able to climb. This simply rejects acceleration. Simply rejects forward vectors that exceed this angle. Yeah. So the idea there is that I can just come down to forward. And if I'm on the floor, force ground movement, I can then dot this vector with my up vector. And then compare that to the cosine of the other one. And if the other vector is greater, then forward just becomes 0. That's my idea there. So that's what I'm going to say. Slope angle check. So I can just say will be the forward dot and yeah, this gives me like the sine. So for an angle of 90 degrees, let me like double check this. So for an angle of 90 degrees, I would get a result, or this is the angle difference. So if the angle difference is 0, the output is 1. Right? But I'm plugging in and I'm saying like 90 degrees. So this should probably be not really inverted, but shifted forward. So if I have this, I can't really shift it forward though. If I say, I guess I would just do cosine of 0, 1, or I have 1, say 2, 3, 4, 45 degrees, 60 degrees. It's right here. Pi over 3. So I'm measuring my forward to my up vector. If it's 1, then this is 90 degrees. If it's 0, it is parallel, perpendicular. It's a flat ground. Honestly, I'm probably just looking for 1 minus, I think. Yeah, this flips it nicely. So I can just do 1 minus to invert that. So I would get a result of 0. So I can say if the output, if I have 0 is my limit, or would I actually just not do that? Hang on. So I just take the cosine theta. Output is 1. 0 is 1. I need the... Or should this be sine? I take the sine of my angle. So if I plug in 90, then I can have up to 1. If I say 89, cosine theta needs to be less than this value. Okay, so yeah, it's sine. Alright, cool. So the slope cosine theta, a forward dot with state dot transform basis y. And then I would just say if the slope cosine theta is greater than or equal to the sine of max slope angle, then I zero my forward vector. I guess I can actually just call this forward cosine theta instead. Now I will have to do some things here. The assumption here is that forward at this point is something valid. So this is probably okay, but some of this stuff is making the assumption that I will be moving forward. So I'm taking move friction and I'm modifying it. Speed in direction, limit in direction, right? So if I dot with 0, my speed in direction becomes 0. A lot of this stuff... Up to forward movement amount. Limit in direction. Yeah, a lot of this makes the assumption that I'm already going to be moving. So how can I stop this early? This is probably like a reorganization thing where I should probably return because the modifiers that I apply, I have this acceleration multiplier. Yeah. I guess I can just set my limit in direction to be 0. I could do that. I say I'm not allowed to move forward. This ends up having a 0 value. Which is kind of interesting because this calculation shouldn't really happen. Yeah, I'm doing a bunch of calculation that I shouldn't really be doing here. And this all depends on forward being some vector. Forward can be 0, and that's fine for it to be 0. I guess I can just say this. If we're less than that, then I can start doing all this stuff. Otherwise, I don't want to do any of that. But I don't like the indentation. The indentation kind of sucks. If I'm stopping, I don't have a forward vector, so I don't want to move. Right? If force ground movement, I have air control, which is fine. And I guess this only applies for grounding, for ground stuff. So I'll see what happens now. Interesting. I can still walk up the walls. .047. I guess I'll see the math for that. It's 86. Oh. Did I trick myself? I think I tricked myself somehow. If forward cosine theta is less than the cosine of... This is the angle between that. So if I say 60 degrees... I feel like I've really tricked myself, honestly. Let me get rid of some of these. All this stuff. So this is cosine theta. This is the value. This is the angle between the two. So if the angle between the two is 0, I have an output of 1. If the angle between the two is 90, I have an output of 0. So I have this be like 89, and then I say step of 1. I have the sine of m. So then I say everywhere that cosine of x is less than the sine of my slope angle. Okay, so I don't understand why... Oh, that's wrong. Because if I say 60 degrees... Wait, is that wrong? Because this should be over here. At 30 degrees, the angle between these two is a large value. Okay, so this is correct. This is correct. Make thread 60. Yeah, what? I'm literally doing it right. So what's the mistake? Oh, I guess the mistake is that I am forgetting to set it. That's right. That's what I missed. Okay. But I think I really want to say like 59 instead. Let's say 55. Because I don't want to be able to climb this slope. This slope, I don't want to be able to go up. Okay, I'm going up it somehow. This is supposed to be a 60-degree slope. How am I going up that? Is it because I'm just walking into it? I guess that's why. Let me double check. This slope is 60 degrees, and I'm able to walk into it somehow. Okay. So I guess what I'm going to do is I'm going to print out... I should be seeing that. Max slope 30 degrees. You what now? What? Should be reading 60. I guess it's the difference between these two angles. Yeah, I mean, I guess it is actually just supposed to be a difference between these two angles, so I do like... So just write 90. What? Why are we doing that? Why am I able to walk up this? I'll print the normal vector. I don't see how I'm able to walk up this. Sometimes it's... What? Also... Is that really air control? I think what I should probably say is like have a slide amount. Like I slide off of it. I specifically should slide off of this, right? I think I can also use this as the spring force. If I limit my spring force to this angle as well, then that's a thing. I'm also thinking there's probably going to be an issue with the stairs. I'll be getting max slope angle like crazy. I mean, not too bad. I'm hitting it, but it's, you know, it's not too bad. And then I got stuck there. Okay. Yeah, I'm stuck. I can't move. Okay. Alright, I think I've got a better idea on how to do this. I think what I do is, if my slope angle is too steep, I change my vector to just be straight into the wall. And then I have to do something with the spring to stop it from pushing me up. Because it shouldn't be pushing me up, I should be sliding down. Or I can just create a slip force and just say, alright, we're on a slip that's too steep, let's deliberately slide down. Right, let's go down that slope. So I just take that normal angle, and I guess I would project it to gravity, and let me think about this. I think if it's let's say I have like a 15-degree slope, and I say that's when I start sliding. I think I just rotate that 9 degrees, and I apply that direction, projecting the gravity vector onto that. Or I say projecting. Mapping gravity onto that vector. And I apply that as an extra force to push me down. Okay. I think that's what I do. This adds a slip force. In the downhill direction. Right? But I do have to make sure I'm not double counting gravity as well. I guess if the spring is happening, then I don't have to consider the spring. But then okay. I guess what I do is this adds a slip force by reprojecting gravity in the downhill direction. So I can change my gravity force. I don't think I'm meant to change. Let me see if I do something. I want to check something. I'm just going to lift myself off the ground. So I just want to check. And what I'm going to do is I'm going to say, I'm going to have, yeah, in the integrate forces, I'm just going to set gravity to something else. I'm going to print total gravity. Cannot assign a new value to a read-only property. Okay. Well, there's that. That answers that question. All right, so yeah, here's what I'm thinking then. So I probably need to just compute a gravity as something else somewhere around here. And now I just search for, whoops, now I just search for total gravity, change that to gravity, change that to gravity, change that to gravity. What are you upset with? Oh, because apparently I do it. Sure. I think I'll leave that one there, but down here, because I need to reproject it. So if we're like this, and I say max slope, and I'm going to reproject gravity. So essentially my idea is I will do something a lot like this. So I take, well, I guess I already have my forward vector, which is aligned to the ground. So the forward, no. I have ground normal, and I have my up direction is what I have. Well, actually, this rejects the slope. But then what I need to do is I need to, I guess at this point, I actually modify gravity by that number. But I do need to run this before that. Okay, here's my thinking. Actually, this is exactly what I should be doing. So I do the slope angle check. If desired speed is like that. Okay. Okay, so let's do this. I don't just zero it, I just take, I'll do this. So I have my up, I cross in my desired direction, I get this vector. I take this vector, I cross with my up direction again, and I get my forward vector. Okay. Forward vector. Wait. Cross with... Wait a second. No. Up vector, cross this. Get this vector. This vector. Cross my up vector. Gets me that vector. The new forward vector. Okay. forward will just take on desired direction. And then I say reproject gravity, I think. Actually, I think what I really mean to say is just have a slip force that is created. So I'll just say slip. Well, it's not really a force. It's a... I mean, I guess it'll be a force. It'll be delted. So I just reproject it like that, and then I will say... and all this is going to drop back out. This should all just drop back out. I'm just creating a slip force. Along the downhill vector. So I'll say var downhill will be my ground normal. What is it? There's essentially it's just a 90-degree rotation. So if my ground is up, I rotate 90 degrees. But how do I make that 90-degree rotation? It also needs to be in the direction of downhill. I can't go 90 degrees the wrong way. Okay, so let's say up vector cross with this vector gets me that vector, which is along the normal plane. This vector... then I guess I can take this vector, cross with my up again, and I'd get... no, that just flattens it out. That's not right. Get the ground normal, cross it with gravity to get this vector. No, I've lost information. So I take this vector, cross it back with ground normal. This vector cross with ground normal does get me downhill, actually. Okay. So if I have my ground normal, I cross with gravity, I get my side vector. I take this vector and I cross back with that, I'll get a downhill. Okay. So I take my ground normal, cross with total gravity, and I take this and cross it back to the ground normal. Normalize it. And then I just say slip equals downhill times downhill dot total gravity. I'll print max slope, and then downhill okay, so I'm just computing that. Gravity not declared. Right, I'm just going back to state total gravity. Okay. We're being stupid again. I'm pretty sure, like, it's gotta be... Okay, hang on. Where exactly did that happen? This line. If not, is not... Here's what I don't understand. Why preload is not getting this loaded. Because if my node is not ready, I shouldn't be there. Null context given. And player.ready. Okay. Yeah. How is this running ready with these being empty? That's what doesn't make sense. Because they're not empty. This is preloaded. What are you doing? What are we doing? That's just some stupid bug. I don't understand what that bug is. It's definitely some stupid bug. Where it's not actually preloading it for some reason before it runs. Downhill is negative, or is positive 0.5, which would make sense. And then negative... Wait, really? That seems pretty high. That seems really high, actually. I'm also surprised by... Well, first of all, this should be always running. That's kind of partially a mistake. So... It's not supposed to be only when I'm moving. It should be... I mean, really, it would be here that I check it. I mean, I guess what I can say is just say, like, do a calculation up top where I can detect. Hang on a second. If I'm on the ground, I want to compute my contact normal, my collision normal, which is just my ground normal. And if that normal is beyond a certain value, okay, that's probably my mistake. Okay, so I'll say this. This should be up here. So this should be my, not my forward, but my, I mean, yeah, my slope cosine theta, grounded direction. It is actually a bit wrong. Okay, so that's gonna need to be reworked a bit. Ugh. Okay. So I'm gonna have... Just gonna call this... Because yeah, I kind of did that wrong. I see now why I have to use sine there, but... Say floor cosine theta. If floor cosine theta is greater than that, which this is just going to be, instead of my forward, I'm using the ground. normal. So my ground normal. So if they're aligned, we're cool. Yeah, so I think I'm looking for something different now. Because I want to flip this around the other way, really. I mean, I guess I can just literally flip it around the other way. So at 90, we're always allowed. At 80, we're allowed. Well, this is what I'm not allowed, actually. So the area shaded is where I am allowed to walk. Or sorry, the area shaded is where I'm not allowed to walk. What? No, I mean, that's just the wrong way around. Because cosine theta is now actually the difference between my up and the ground up. Actually, it's not the difference. It's how aligned they are. So at 0 degrees of alignment, 0 degrees different, we're fine. If I set this to 80, then we're fine up to 10 degrees of disagreement. And once they are... Oh, wait, no, that is wrong, isn't it? I'm confused now. Because now I'm taking my ground normal and I'm dotting with my up vector. This one does have to be like this because it's which way you're traveling. Actually, I guess that's not which way you're traveling. Oh, the direction of this body along the plane of the ground. Yeah, I mean, this is the direction you're traveling in. No, this is supposed to be... Oh, now I get it. I get it, okay. I have just some mistakes in reasoning for this. So my slope cosine theta is actually the direction that I'm looking in, not the direction I'm traveling, or not the direction I'm actually moving. What I've computed here is my relative velocity along the ground. That's what I've computed. Which means if what I really want to do is I want to take my forward vector and align it to my up vector. If my forward vector is too high, yeah, so what I really want is forward. Okay. So this is my slope cosine theta. So if I am at 90 degrees, so my forward is whatever, and this is that, and I dot, I get 0. If, as this increases, the slope angle increases, so I get a higher value. So if my slope cosine theta is positive, this means I'm traveling up, which means I should be taking my... What I want to know is how high this angle is. So I guess this should actually be a cosine now. Okay. This should be a cosine now. Alright, let me check this. I'll just block that out. I'm not doing anything else. I shouldn't be doing anything else. Alright, if false and so I don't even do that. Okay. Let's go over here to a slope. Alright, so it's still... I guess it's actually still kind of wrong. Oh, man. Right, okay, it is actually meant to be a sign still. It is still meant to be a sign. But yeah, I should just be... Okay, yeah, that was right. I'm supposed to be using my forward, not my ground direction. Because it definitely is the case that I said earlier, where if you're like... if you're traveling backwards on something, then... If like my relative speed up a hill, if my relative speed was up a hill, and I were to press down, technically I should have a lot of stopping power there because I'm applying a huge forward vector. But it would actually be reading my forward vector as if it'd be treating it as if I was traveling up the hill. So my speed would be limited as if I was going up the hill instead of this. And I just need some like friction calculations that are bit better. 4.9. Was 4.9 when I typed in? Yeah, okay. Yeah. So that part needed to be fixed. This is my floor cosine theta, so this is that angle. So I take my ground normal, dot it with my up. When they agree, it's 1. When they disagree, it's 0. Which is 90-degree angle. So if I take the sine... Yeah, so when they... This is the floor normal. This is my up vector. When they disagree... Actually, I should probably do it like that. No, I don't know. Like this? I don't know. All right. If my normal and this agree, the result is 1. Okay? The result is 1, right? When they agree. When they disagree, this is an extreme slope. So, I mean, yeah, I think it's just, I just flip this sign, right? And this is all walkable. But this does the wrong thing. If I plug in 0, so I'm actually looking for cosine as well. So these are all walkable. As I get up to 90, they can disagree greatly. Okay. Alright, so yeah, I flip it to cosine. And my calculation is to flip the sine. So I guess if I write it as when am I slipping, these are the values I'm slipping at. So less than or equal to. So this is when I'm slipping. Slip angle check. This will redirect my forward vector. So force ground movement. So like, let me just do a check here. I guess you could set a I guess you could set a boolean that's like slipping, and this is like a recalculation. So now here I could just say this, and I say is forward slipping equals true. And just say if not is forward slipping. I can do this calculation here. If we're not forward slipping, then we do this. If we are forward slipping, then I would be running this instead. I guess I say stable ground. So I just skip that if I've already computed it. And I guess I could do a shortcut here. And I guess what I could probably say is actually just say wants to move. And shortcut that. Yeah, let me just say this. It's desired forward. Right? Those all look good. This is our forward slipping is set to true. And then I guess I just do this. I set that to true. Downhill. So I'm always doing this if I'm slipping. And then I guess I can print it out again. This is now, what's the problem here? Forward floor cosine theta. So I should always be printing it when I get on this. Cool. Max slope reads 30. I think it just means I just don't do that anymore. So this is the disagreement. So if I get on here, oh, it only does it when it's disagreement. Okay. So I have my slip, and this is an acceleration. I'll just leave the print there for now. And what I will do is down at the very bottom when I apply my motions, I will add total gravity plus slip. Interesting. This should be an acceleration, though. Mm. Maybe it's because I'm pressing into the ground extra, so I probably just take this vector and then I discard the portion that aligns with gravity. So I slide gravity out of this. Does this work better? Yeah, what downhill is... Huh? This didn't even do anything. What? Oh no, I'm printing... Wait, hang on. I'm printing... No, I need to print slip, not downhill. Slip. What? Okay, so I've computed... Downhill is computed correctly. But then, yeah, I want it to be... So that's slip. But then I just want to remove... You know what, let me just say this. If state dot total gravity is 0 approx, not. There we go. Like, it should be really slippy, I think. But I'm a bit confused why it's kind of not. Yeah, like, why do I fly up that? What am I getting wrong here? Should I just not be sliding out gravity? Should I just be doing that? That makes it slidier. I think I have to for the spring, because otherwise I'm just adding downward. I'm doubling up on gravity, right? Oh, hang on. I think I do get it. Because it is still like on reprojected gravity. So I need to have alright, I gotta take the dog out. I'll be right back. All right, I think what I'm missing here is that I need to additionally subtract what I've added as slip from gravity. So instead of sliding out normal or sliding out gravity, I want to take this value and make that my gravity, I guess. I guess it's more the difference, right? Oh no, this is, yeah, okay, so this is what my gravity should be. So what I could do is make it so that I take my gravity vector, I've I guess take my ground hill, my ground downhill vector. I've done it with that, so I get this vector just pushed over. And so I can take gravity dot this as my difference. So I'm going to take this, copy that. So this is essentially the length of gravity, the length that gravity should be. This times gravity downhill. And then I want to take this as a reduction to gravity. So right here, I know gravity is negative 9.8 and my slip is negative 7.35. So this means I want gravity to be reduced by whatever is needed so that gravity becomes negative 7.35. So what I can say is I can say, then add I guess I can actually just add gravity, right? So this is my new gravity, and I can just add gravity. But is that actually what I would do? No, that's what I want gravity to become. So if I have negative 7.35, if I add gravity, I have a plus 0.2 something. And when I add gravity back again, actually, yeah, I think I just do plus gravity. So my slip has like a plus 2, which once I add gravity in, then okay, sorry, I'm supposed to subtract gravity. So then once I add it back, I mean the slip is like still nothing. I'm seeing, okay, so I'm seeing something weird happen. So my slip says like 1.6 there. It says 4 here. Man. Yeah, stopping is going to be messed up again. This is like another problem that's coming up where stopping is just this wasn't so easy. I mean, I was thinking I just take my... Actually, you know what? I think what I really do is I take my forward vector. If it's too steep, I essentially have to like reorient it, right? Is that what I am supposed to do? I could just reorient it to be like perpendicular, right? So I could just say, all right, take my forward and then like project it back so it's like flat, right? Yeah, treating it like a wall. I guess that's what I mean to say, right? Then I could also do an Excel multiplier. I can modify my limit and my Excel multiplier to be that, the dot between my forward and where I've reprojected it to. Or forward can just be a shorter thing. That's also possible. Though it probably shouldn't be because I'm still treating it like it's a normal vector here. So and then that also doesn't work because then once I get in here, then my limit is also multiplied by a loss. Which I guess is probably fine. Alright, my Excel multiplier is 1. I'll just do this. I just do multipliers. Alright. So here's what I say. I say my slope angle check. If I have a desired forward, I want to reproject it so it's so if I have my ground normal in my desired direction and I do that, I get this vector. So I take this vector, cross it, because I basically want to like mirror it. I guess actually what I can do then is I can do this. I can say my normal, I can take my negative thing, dot it with that, and now I get a vector that way, right? So I can flip that. I guess I can also do this, and I can say dot with... No, that one doesn't change. I have to flip this one. And then this one dots, and I get... No, because then I get the wrong thing, actually. I still get the wrong thing. I have to do it with my forward somehow. Basically, I'm supposed to treat it like a wall. I can have a slip, and I need to treat it like a wall. The part that's stupid is that I'm not accelerating downwards. I should be accelerating down. Why do I not accelerate down? That's what bothers me. I don't maintain that acceleration. Is it because of this? I do take off too much of it or something? And so I start detaching from the wall, so I lose that acceleration down. Because this should just be constant acceleration down. Notice, because I move down, and then my spring applies an upward force to oppose, but I still move left. Oh, is it actually friction stopping me? Maybe that's what this is. Maybe that's what's happening here. Friction is applying. Is the stopping force. You look at the big friction value. Okay. So it is just a problem with stop. I can turn that off, which is just... I guess what I can say is if not is forward slipping and deceleration is greater than that and ground velocity is 0, so now I don't apply this if I'm slipping. Okay, so for some reason it's still applying. I don't understand why. That literally doesn't make any sense to me, why that's happening. So does this mean I'm not setting the value correctly? Oh, if has desired forward. I just literally set is forward slipping to be true, no matter what. Now, let me just say is slipping. Not is forward slipping, just is slipping. If not slipping. So if we were not slipping. Okay. Oh my gosh, I can still run up at incredible speed. Alright. So something weird is definitely going on. Let me just take that bit away. Okay, and then I do need to, yeah, okay. So that's working there. I need to, kind of take my forward and I think calculate the stable motion. Actually, yeah, I guess I still calculate the stable motion. Alright, so maybe I don't do this. Maybe I leave this. Wait, why do I need forward? I actually don't need forward there. Okay. Let me say this. Put that. I turn on slipping. Then in here I have this check, so I say if is slipping, I run this, otherwise I run this. In addition to that, I say my limit in direction will be multiplied by, I mean, I guess I still calculate this, and then I say if that, I want to say do this cross to get it straight, and then I say if I'm slipping, I want to calculate how much I am slipping by, so I want to say I guess what I mean to say is to take this vector, so I'm going to say slip forward. Hey, I am so trash pie charm. No, this is Godot. Slip. This is the vector 3. This could be this. My limit in direction will then be I guess I'll say slip multiplier float. Be taking dot with the slip forward. I think that's about right. Maybe I want to say is slipping first, and then I can calculate this stuff. And then otherwise I do some other things. But I need this for both. I didn't know, thanks. How are you doing? I'm doing alright. I'm trying to get slopes beyond your max walking to be slippery, which is difficult, and this I really wish that would just stop happening. Oh, I did this. Okay. So that didn't do it at all. Why not? Because this should be like a small value. Oh, it's only when I'm going forward, that's why. I've done it again. Okay, so do this. Take this out. If as desired forward. I guess this is also, well, a pretty wizard thing to me. You're learning Gen AI. You say wizard thing, and then you're talking about the cutting edge of technology. That's interesting. I'm just writing if statements and multiplying things. Well, yeah, no, this is supposed to only apply then. Okay, so what did I do wrong? Forward is slip forward. Okay. And then slip multiplier should be that with this. Okay, so yeah, now I'm just confused. Oh, this is dotting with that forward. That's probably the problem. Which I've changed it. No, this should have been fine. I'm confused. What? Okay, so I'm accelerating at half the pace. This should be nearly 0. It's kind of not nearly 0. It should be like really high. But yeah, what? That doesn't make any sense. That's not right. The order of this doesn't matter for dot products. They're both normalized. No, that doesn't make any sense. Because a dot of like 1 degree would look like this, which this is what the difference is, because it's an 89. Wait, what is the angle of this wall? It's 80. Oh, okay. Alright, that's right. That's my interest. I'm gonna become a game dev. Very hard. A Gen AI, man, that's I mean you're like looking at something easy and thinking it's hard, and looking at something hard and thinking it's easy. So I don't, maybe you just lack the understanding to realize that. So keep learning, man. Please. You're gonna realize making games definitely easier than training an AI. I guess I guess this is probably what the problem is, isn't it? I have to compute this. All right. Let me compute it up here. And this needs to happen there at that point. That needs to happen right there. It's really windy. I don't know if that's audible. Yeah, that doesn't make any sense. My speed in this direction should be multiplied by my limit in this direction as, I guess it is multiplied by half. Ah, sure, yeah, that makes sense, I guess. What's going on here? I'm still able to walk up it. Alright, let me see this. Yeah, so sliding down looks pretty good. I'd like to try to slide down this, but I can't even walk up it. Which is fine. No, my slip board is actually supposed to be turned sideways. No, I actually get it. I actually think I understand it. Okay, so my forward doesn't become, you know, mapping it down straight. It becomes mapping it down straight, but then projecting back as if it was a wall. So I slide out. I need to treat it like it's a wall. I guess what I can do is I can take the contact normal, I can zero the y, and then I normalize that vector. Then I get a vector pointing straight at me. And I can use that to slide out of my forward. And then I normalize that. And then that dot becomes this. Okay. It is a normal vector, but is there a case where all of it is oriented up? I mean, I guess I can just say... Yeah, just do this. Normalized. So I take this, I take my slip forward. Then I take my slip multiplier will be my slip forward, I think, dot with the wall normal. No, I mean to actually take this and slide out. Thought it with that, and now I get... Now I get a proper slip multiplier, which should be really small when I'm looking straight at the wall. Straight into it, I can't even go. I go on the side a bit. That's fine. I still have the weird springiness being a bit of a problem, but this is better now. I can't walk into it. I can still climb though. But at the very least I can't like really walk into it. If I go at an angle. It should be that if I look straight at the wall, my 4 just totally slides out. Well, I guess not really, it's a multiplier. If I look straight at the wall, that just becomes 0. So I say my acceleration multiplier is multiplied by a value near 0. Okay. This is working a little bit better. I can't walk up this. Reconnected. Did I? Reconnected, you say? I don't believe it. Because Twitch doesn't load it, and then Twitch never loads it, actually. In fact, Twitch never gets the stream back. Because it's just a broken website, broken buggy website. Okay, it's back. Am I really back? I hear myself? I hear it. Okay. Not sure what happened with that. And I think what I really like to see is that because if I stand still, the slide works pretty well. I get up this, up the wall, then I stop. That's pretty good. But ideally what should have happened is the spring is kind of... Maybe the spring just needs to be stiffer. It is a genuine problem. A stiffer spring. I'll see if I can tune that a little bit. Not a lot, but a little bit. It should just be using default values. What? I'm a little confused at what has happened. Yeah, anyway, those are default, so... to 2.0, and let me bring this to like 2.1. And see. I still detached from the ground, so... Epic should really be... Does it really need to be like a lot higher? I should get this little bounce. It's probably just like the stiffness needs to be... Yeah, that's kind of a problem. The step up is weird now. My thought was if I make the spring stiffer, that will work, but I'm actually still able to accelerate up that. We'll change these values back to what they were. Let me try 2 though. Maybe if I increase it a little bit, I can fix this crouch thing that's happening. Yeah. That fixes that. Okay, I'll just leave that. It is all a bit weird. Maybe I bring this back as a redirection to gravity. Maybe this helps it. No, because the spring is tuned for that kind of impact. So when I take it off, then the spring behaves strangely. But there is the thought that the spring should be considering this ground normal dot the spring direction. Or is it spring velocity? I don't think so. I mean, this all... Like, I am taking off gravity. Maybe what I meant to do is... Because this still includes gravity, maybe I should just be taking off. Or on the slip, taking off gravity now. So take all of this and then slide out gravity. Maybe it actually is that. Hang on, I think it's probably this. I think I should slide out gravity there so I'm not double counting it. But this slip forward is just a multiplier. So I think what I really do is I just leave that. I'm just using it to calculate that. I'm not changing it. So my forward is still going to be up when I'm on here, but it's going to be so reduced that I shouldn't really be able to climb up this thing. There's just like, it's just the bounciness of it kind of sucks. I wish it wouldn't do that. Alright, bring gravity back. Double gravity. Yeah, okay, so I like literally can't climb up this thing like that. Oh, this is probably right, because I do need to redirect gravity. Why did I launch earlier? I just launched earlier. Honestly, maybe it is just like more damping if I just have more. Let me see. See if making it a little bit higher does anything interesting. Yeah, that bounce is kind of crazy. There might be a problem here with this cosine, I'm thinking, because I feel like this is supposed to be pushing less when I'm at a steeper angle, and it feels like it's not actually pushing any less somehow. It seems like it's just not. Maybe it's more like this. The spring is meant to be multiplied by that value instead. You know, I think that actually probably is it. Let me comment this out and let me see if this should go up here. Multiplied by the ground normal dot with the spring direction. It's strange. I'm gonna see if I can get myself stuck on the stairs here. If I try and walk and try it. I mean, that happens, but it's not really like... I mean, sometimes it seems like theirs might be a misstep. Like if I stop. But this is really steep stairs, and this is probably like the worst kind of stairs to have. It seems like it's not really possible to get stuck on the stairs. Yeah, I can still make it up the stairs using the spring as a pushing thing. This might be a better, this probably is a more appropriate calculation for spring though, by putting that on there, because I see now that this is dotting with spring direction and ground normal already. And so I should be doing it up here as well. But the bounce does kind of suck. It's one of the bounces pushing me off the ground. That's kind of the problem. Let me see this in slow motion, I guess. Yeah, this doesn't become a stable configuration, is kind of what the issue is. This should stabilize really quickly, but it doesn't. Maybe it's maybe the slip is actually the problem. What if I just take off slip entirely now? Well, I need slip for whenever. But let me see if we... Yeah, what if I don't do this? What if I'm moving? Only when I'm not moving. So I'm moving, I don't do slip. Okay. So it is slip maybe being too powerful or something, or not also taking into consideration the forward. So I guess what I do here is if I say I am slipping, maybe I just say, well, I really think what I should do is just not allow, I feel like I should just reject forward. But then that doesn't treat it like a wall. I want to treat it like a wall. Yeah, I'd like to treat it like a wall. Which means forward should be just projected left or right. I shouldn't be able to go up. That's the problem. Okay, so I should just project forward to be left or right as if it's a wall. So if I'm walking straight into the wall, it'll just come down to 0. But otherwise, it's going to be one of these directions multiplied by, or like a parallel direction. So I guess what I can do is I can take forward. The problem is getting it to be directional correctly. I guess the forward matters. So the forward, that's the right. I'm trying to think of like how I can orient this so it's right-handed. so that it comes out to be proper in the right direction. Okay, no, I think what I should do is I take forward. At this point I take forward. Where do I use forward again? I use it for the speed and direction calculation. So I think I take, yeah, so I think what I do is I take forward at this point. I call my speed in that direction, my limit in that direction. When do I use forward again? I use it here. And I calculate move friction. So whatever though. Yeah, I think my slip forward is that, and then I slide out. No, I think I actually get it. So it's in a straight line. I slide the wall normal. And I guess I can say if forward normalized. I guess this just becomes 0, so then I wouldn't do it again. Yeah, I guess that's fine. So let me try that. Oh yeah, air control is allowing me to kind of do that. Maybe what I can say is air control can only activate if I'm in the air for like a certain amount of time. Minimum time in the air to have air control. Maybe it's like a ramp. I calculate how long I'm in the air for, or how essentially just how long I'm free falling for. And I mean, what I could do as well is treat it like a hard collision, and I could slide my entire velocity. I could just totally slide out my velocity. That's what happens on a hard wall. I could just do the same thing there. I could treat a slight slope as if it was a hard wall. That's what slip is supposed to be. That is what slip is supposed to be. let me do this. Let me see what happens if I turn off. I set air control default to be 0. Which I'm just operating on defaults right now. Just say 0. I just bounce off it, right? Maybe what I'd like to do I can kind of treat it like a hard impact, which would prevent the spring from really contracting. So if my spring collides and it hits something that is to be considered a wall, then I end up calculating a spring force from its contraction immediately. Because I need to. But then I think I would like to slide up that wall as best I can instead of applying a spring force. So maybe that's it. If I can stand on it, I can stand on it and I can do spring forces. If I can't stand on it, I treat it like it's a rigid collision. And I essentially just do sliding and stuff. So I keep the spring's current length. I guess I mean I guess I can still recalculate that length, but then I just slide. I should slide along the wall. I mean, honestly, probably what I could really do is I could just say, if I get slip, I set my spring to be 0. I just turn off spring entirely. What would that look like? I mean, what I could do is I could lock in the spring force. So this is just computing. This is saving an is slipping thing, which can be used down here. Maybe that's what I mean to. Then maybe that's what I really mean to do. I mean to like lock in the fact that I'm slipping. Okay, let me say this. And I guess this should just come up here to be it. Need this. So here, I get the ground normal, and then I can do a slope angle check, and I can update is slipping at this point. And then is slipping should also just default or reset the false. When I detach from the ground. But then right here, if I am slipping, I would like to treat the force as if I am... I think I just want to treat the force as if I'm fully extended. So I say my offset is going to be... Yeah, I can just say length is 0, right? Well, I guess I can actually keep it written like this. I can say if is slipping. I guess if I can say if we're not slipping. I say length is equal to max length. So I pretty much just stop applying the spring force. Well, I guess not really. Well... This can actually come back. I'll put this up here. And gravity is not approximately 0. I'll just print slip now. And then I subtract gravity. Stop doing it. It's real, it's there. Why? Like, why does it do that? What does it think is wrong? Um, I think it's a little bit better. But it's not really it's not exactly the result that I was looking for. Because if I touch a wall, that's at like 80 degrees. I mean, I guess that is 80 degrees. All right, let me turn air control back on. I mean, this might be good enough. But the slip stuff is making me a bit annoyed, a little bit upset. That it's not so. I mean, I'm not even getting, I'm actually, air control is back on, but I'm not even getting any amount of air control to work with. So yeah, I really hard slide off that. Alright, let's drop me on top of it. And by drop, I mean just set me very gently on it. Okay. And then I'll do slow motion when I load in. Oh, I commented out immediately. Duh. Okay. So the spring isn't really detached from the wall a little bit, but that's fine. Yeah, the spring is, yeah, as I expected, non-functional. This is better, for sure. I saw air control up here. Am I changing the vector? Oh, I definitely am, yeah. Okay. This looks good, I think. It does make me a bit sad. It's, this is kind of a convoluted solution. This requires too many things to be working together. I essentially turn off the spring, but then I'm redirecting gravity, which is part of it. That's a big requirement. I can't really walk up it. It's a pretty hard wall. This is like 5 degrees more than what I can do. I'm bouncing a little bit, but that's fine. I'm okay with that. As long as I'm not like bum 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 like rapid fire. That's more annoying. Trying to do steps like this. It does seem like that, right? But that's, I mean, I'm trying really hard to do this. I'm trying really hard to make that slide happen. And it kind of doesn't really want to happen. Because the steps aren't steep enough. If the steps were steeper, I mean, that's also probably part of it too. If I literally made the steps steeper. Yeah, like I'm never gonna get stuck on the steps, basically. I shouldn't get stuck on these steps. Let me go push my box, see what happens when I run into it. Push it up a wall. Nothing weird's happening. I'm not like flipping out or dropping into the ground with some high speed or anything like that. The movement friction vectors are kind of insane, but whatever. Slopes still work, ideally. This still works. Whoop. Go up. Okay. It doesn't make me happy, but it's working. I don't know. I don't know. It's this part. The fact that I have to redirect gravity. Let me note this. Note when slipping, the spring disables itself. Redirect gravity in the slip direction to prevent falling into surfaces while slipping. To prevent the spring from falling into surfaces while slipping. And let me go back to that other wall. Back to this one. I mean, this is kind of like, you know, ultimate trying to mess with stuff. Right. Like, I shouldn't have an 80-degree wall anywhere in my level. But if I did, this is what would happen if you walked into it. You would fall a little bit. I don't know, maybe if I'm slipping, I can actually contract the spring, but have it push back, like, fully. I could have that happen. and I'll do what to do. Let me just see if that kind of makes it better immediately. Let me just see. Because I know what I should do. I'm modulating my spring by its direction already. But then the spring direction should probably be ground and normal instead. So I just want to see if ground and normal is better. Now I can't even walk up the surface, actually. It like totally rejects me. Yeah, wow, that's kind of nuts, actually. I mean, it doesn't push me away anyway, so... yeah, just leave that. I could also probably limit the stairs so you can't just go flying downstairs like this. Maybe stairs should be like a different kind of, like a special kind of collision thing. Which is fine. That's setting a flag on some collider that says like, hey, these are like technically stairs, so when you go down them, limit it as if you're going up. Right? Have all directional limitations. Treat any motion relative to the ground as up, right? And a slope can be treated like a slope. So I can go up and go down them faster, but then stairs would be different. I can't go down them faster. And I mean, that would basically just be putting them on a mask that says, like, these are stairs. And I can make it always treat as a decline. Alright, I'm going to put that... I think I probably need, like, an actual miscellaneous to-do list or something. There's some ideas here. Create a collision layer named stairs. And check if the floor layer matches. When it does, treat any normals as uphill normals, so that slope effects always slow the player. This prevents stairs behaving like down ramps. All right. That's for the future, though. I don't want to do that now. Is it all done? The slip is pretty good, right? I have air control turned on. I walk into it. I slide down it without really messing with the spring too much. Like, this is an egregious example. You know, movement's a little weird looking here, but I think I'm okay with that. This is really the kind of thing that you walk into it, you do that. Maybe you back, oh wait, hang on. If you like back up into a wall and then released, you kind of fall a little bit. I mean, honestly, this is probably just like, I could do a ray cast, do the first collision, and if it's not a floor, ignore that object and cast again. And then see if I get a better floor. If I get no floor, then I use the other one. If I do get a floor, then I use that one. Which means when I do this, essentially I start ignoring that and I just treat it as if I'm walking into flat ground. So let me check that. Let me check a thing really quick. Yeah, okay, so the collision normal for the ground is still here. Right? It's still there. And that's also there too. I could do that. Because these end up having different RIDs. Right? These are different things. This is one big collider, so I would actually just kind of ignore the whole thing, which is probably not what I should do. But then I ignore that, and then I cast again. You know, I wanna do that just to fix this, because this is kind of an issue. Because I feel like, you know, really, in reality, if it's 2 feet, you're not planting both feet firmly. You're not a spike, I guess. The character controller acts like a spike right now, stopping at the first thing it touches. So yeah, let me do this. If I'm slipping, I will attempt to do this. I will say, and then this I can just leave it like that. I can try to get a better cast. So I will recast, ignore this contact and recast for a better surface. Right. So I will do get collider RID from 0. Add exception RID. Add exception. Yeah. RID to ignore. Remove exception RID. Yeah, okay, so I can just do that. Updates the collision information shape immediately without waiting for the next physics process call. When the shape or its parent has changed state. Setting which is not required for this to work. Force shape cast update. So it should just redraw it. Then I can do if shape cast is colliding, ground normal equals shape cast get collision normal 0. And then I can check this one. And if this one's okay, then I'm good. I still want this slipping to be true because, you know, my initial contact is sliding. But this can still be used for a better length calculation. So I can still apply a force as if my length is actually colliding with that at the bottom. Or with the portion beneath me. And this all doesn't matter. Okay, so I'm going to bring this down. Calculate this. Slipping is false. This slipping is true. I recheck it. So I can just grab this. Paste here. So if this is better, then I can say, all right, now length can be this calculation. You know, let me just say this. Let me just say, yeah, all right, let me make this a Boolean. Use contact length. True. I'll just set this to false immediately. Then I can reset it back to true. And I say if use contact length, what does it say? It's max length. So I'll slide away, but I still like maintain my height. I shouldn't like jump up and do that. But at the end of this, I have to shapecast, remove exception, RID. So the next time we'll keep going. Alright, so I'm maintaining my height there. I'm not dropping into the ground. It's quite jittery though. But this is way better. This is so much better. But unfortunately it seems like I can't move when I get stuck in the wall, which is a bit weird. Yeah, okay, so that's kind of a big issue. Oh, wait, it's throwing errors. No collider found. Uh-huh. Oh. Alright, let me check where Shapecast is used. Yeah, okay, so it's kind of like... Alright. So I need to do some stuff here, where I guess I pre-calculate. I grab this first. So let me grab all of this first. Anywhere that I read from it, I need to grab first. That's all fine. That should be fine too. Get collision point. So I may need this to calculate some things. And this will be, I guess it should really be hit position, not hit point. And if I get another one of these, then I update this stuff. So this will be a new one to use. So ground, what would I be equal to shape cast? Hit collider 0. Hit position is now equal to just the exact same line, get collision point. Right, so I just update those. And I guess I can say if this is... Oh, actually, maybe it's more just that if this is true, then I collect these. No, it's just whatever. Alright, no bug now. It is a tiny bit jittery. I think it's probably just because of... Yeah, what is... Oh wait, I still have errors happening. The normal vector 0 must be normalized. Ground normal. Oh, is this the problem? I need to grab ground normal again, or something. Yeah, ground normal is updated again. Well, no, because it is updated. So why is it being like that? Oh, I guess because the ground normal points straight up. So when I do that, okay, no, this makes sense. So I guess I just need to say if I am slipping. No, I think I just don't update the ground normal, really. I think that's all I do. No, the ground normal has to be updated for the spring calculation. But it should not be updated for the other ones, because that's requiring slip stuff. So I use ground normal for that, and I use it for all of these calculations. Ooh, I actually use it a lot. Alright, so then I guess the mistake is that slipping could still have... could have a ground normal that's not 0. Which, I mean, I guess I always knew that. Well, I guess is slipping. Yeah, I use this to push myself downhill. I guess I can add this to like as a spring force. And I add it to the spring force to push myself downhill. Maybe that's just what I do. Then I do this. I mean, maybe what it really is I mean to be using a wall normal, and the wall normal, this can be added in the spring part. That's probably okay to do. Because it's like a ground force. I mean, yeah, that makes sense. It's a ground force. This part, I think I probably just have to provide myself a wall normal. So that's probably what I'm really looking for. I'm really looking to give myself a wall normal. So I guess let me do that. I guess I'll just call it wall slip normal. Or a wall slide normal. Okay, so here's my idea. This part can drop out and can be moved into ground forces. Okay, so somewhere in here I need to do something with that. Like here, maybe? And this would be that initial slip thing. I guess the slip normal is just the if slipping is true, then I say so the current ground normal, so I stash it and I can update it again. I can cut this out. And because spring force is going to be multiplied by inverse mass, just state inverse mass. I can just multiply by mass. This is basically pushing the player away from the wall. And then up here, instead of wall normal, what I do is I take my wall normal is going to be my wall slide normal. It's still really jittery, but at least it's not, no more errors. I mean, it is like really unstable. So, I mean, I'm not really sure what's actually happening and why it's doing that. I mean, it just seems like my friction's going insane. Yeah, I'm getting like this really high thing going on. Is this vector move friction? Honestly, I can probably just say if not is slipping. So I just ignore this if I'm slipping. So maybe that just goes away. But it's weird because I do press into it. I didn't think I should press into it. It definitely is because I get this like one, it's like a single frame that I am allowed to walk directly into the wall. Because now I don't have a collision with it. That's allowing me to like jump up into it. Oh, there's also that. I can just jump up walls forever. But it's really hard to do. This is a little bit better. I still have, it's better because it's not like this constant jitter that's happening. It kind of looks like it is a little bit because of debug shapes on, so let me just turn those off. So we're not looking at that. It's definitely better. That feels thoroughly slidey. just trying to like mess around with the stairs enough and see if I can. Yes, I mean, as long as they're not too steep, the slip doesn't really do anything. This, though, is odd, right? This is kind of an odd interaction that's happening here. I guess what I could do is I could project myself forward and see if I would hit a wall and then just slide instead. That could work. I don't know. Let me see if... Alright, let me... I'm so glad I can see these debug vectors, by the way. It's actually making it really obvious when stuff is going weird. Uh-oh, there's gonna be a freeze. Alright, we're back. I don't know why that happens. Alright, what's the spring doing? So the spring does apply a really high force when I start walking into it, which is not what I want to see. So I'm guessing somehow I'm actually applying it anyway? So use contact like this true. If it's bad, then I say don't do it. And then I add that as ignore, and then I cast again. And then I hit the ground in the same way. And then if we're okay, then we're okay, right? Drop it as an ignore. Maybe it's a discontinuity because I say we're at max length. And maybe what I mean to do is just remember the last length that I calculated. I don't know, because it's use contact length true. And then I say we can do this again. Okay, I mean, I guess what's actually happening is I probably hit the wall. No, I'm actually not sure what's happening. What's going on here? Oh, I'm also just getting... I am also actually getting stuck in the wall, too. So that's kind of a problem. Damn. Maybe what I mean to say is if I get this, my wall slide normal is ground normal, but if I come back, then I say wall slide normal is... No, I don't want to do that. I don't want to do that. I want to... I don't know, maybe the trick is just I actually ignore that collision entirely. If I'm still touching ground, but I'm hitting a wall, I just effectively treat it like a wall. But I make it so the spring can't push me up the wall. Let me try that. Let me just try turning off is slipping at this point, and see if that's enough. Perfectly stable on that wall. You can still kind of slide up it a bit. Really? Wait, really? Wait, really? Was that the solution? Alright, drop me on it and let me try to walk up it. Yeah, I tried walking up and I couldn't do it. Really? Okay, let me make a slope. Well, I mean, I can just make a, I will call this, the slope wall. And it will be a rising slope. So I can just have a... Jeez, please. Those really hard to type things in there. You exist on collision, you are visible, you're on static. I think I don't need to have anything else. Yeah, it's just static. So turn that off. Slope wall. And I can just be back here. Blue. I should probably do this. So have you be 20 meters long. Try to make it like a gentle slope. Maybe more like 30 meters long. 20 might be enough. 20 is probably enough. I'll make you 10 meters tall. Well, I mean, essentially what I'm going for is a big half pipe. So probably I will just do 25 and 25. And then maybe be 5 meters wide. Why not? And then I'll have a big sphere. Sphere? I mean cylinder. Flat, radius 12.5 meters, height 6 meters, operation subtraction, actually radius would just be 25, and then it will drop back 25. Or I guess forward 12.5 and up 12.5. No, up 25. All right. And then I just make the sides be really, really high. I also have a very high side count. 64 is the max. Okay. Then I guess it's 64. And I guess I'll move it like up some amount and then back some amount so there's some thickness left. The surface. Right. Right, there's the slope wall. Okay, time to climb the slope. And that's the limit. And it's pretty stable. Cool. Yeah, this is nice. I can literally, that's just, I mean, I don't know. It just literally treats it like a wall. This is a little bit odd. Maybe it doesn't seem quite correct on the angle, perhaps. I think what I should do, because it's actually, if I get stuck, if I get on this, I actually can't walk out of it. Here's not so bad because I detach so quickly. I mean, it's probably whatever. Honestly. Can I make it? Nope. I think I am okay for now with how slope works. There's still It's a little bit tweaking. It's way more stable. This is way more stable, just turning off slipping. In treating it like it is a wall. It does seem like I probably can get stuck on it though. So I guess maybe what I should say is not quite doing this, but checking to see if my forward is even slightly aligned with the wall, I use full forward. I don't do any slip stuff. So I guess I do this. So I would just do a dot. So I say if wall normal dot forward is greater than or equal to 0. I guess I should really say if it's less than 0, so they're not aligned. Then I do all this stuff. And then here's the test. So I will go into slow motion. I jump up here. I can't walk, but if I go down, I can go down, right? So my vector is clamped, but then when I start turning, it goes forward, right? So I can still walk down the wall. Also the jumping, I'll figure that out, but well, why am I not slipping here? Oh, no, I'm slipping. I'm guessing I was standing slightly on top of the other thing. Yeah, if I stand here, it should be fine. I can stand on this. It's only once I start going down a bit that I should start slipping. Yeah, you can see my forward vector dropping down. At this point I start slipping. So this is something like I get here and I can still walk off the wall. In fact, I think what I really should do is just not... If this is the case, then... Yeah, probably what I really want to do is compute the slip forward. And then say... Because when I am on that wall and I do the forward, you saw my forward was like really far down. I mean, I don't know, maybe that's fine. Maybe that's just fine. I just leave it like that. This is definitely better because that was a bug for sure. That if I'm on the slope, I can't really, you know, I'm locked into a slide and I can't run off the wall. Honestly, I think that probably is not correct, though. I think what I should say is you bounce off the wall. So my forward vector will still snap to this. But if I do that, then I do this. Otherwise, I say... forward is slip forward. Well, actually, I think I just do this. I'm setting it no matter what. but then I would do forward, forward slide, wall normal. So if I stand on this, my forward vector goes off the wall. So if slope is too steep, I kind of like jump off it, right? So there I'm stuck to the surface. So my forward is like taking me off into the sky, or just off it. Let me jump up this. Yeah, okay. And I'll say if forward is against wall, do additional speed reductions. And clamp forward to be perpendicular to the wall. Right? Okay. And jumping is being a little bit weird. I think I may want to actually have this happen. No, because I need forward. But then if I'm doing that slip thing, then it's snapped to the side, which is a bit annoying. All right, I don't know. This is way better than it started. This is already way better than it started. I'm like actually perfectly stable now walking into walls. I don't get stuck on them. Slight slopes. There's no bouncing happening. There's a bit of a bounce when you first run into it, but you know, that's whatever. And then when you're going down, you kind of push off the wall a little bit. Okay. This is way better, actually. This I'm happy with now. I'm actually really happy with that now. 3.5 hours in, and I'm happy with wall slope, which was actually, this was way harder than I thought it was. This was a lot more than I thought I needed to have. I thought I was actually just going to be, if angle too high, say no to forward. But then that caused, this is really nice. I actually like this. I don't do that weird bounce in, push off, all this stupid movement against a 80-degree slope. I just hit it and I slide and I come back down. This is so good. That's really good. If forward is against the wall, do additional speed reductions and clamp forward to be perpendicular to the wall. If forward is against wall, do additional speed reductions and clamp forward. Yeah, okay. Alright, yeah, I'm actually totally happy with that. That's really nice. Get Godot game. If staged. If whoa, that's weird. Add a slip force. Spring I increase spring damping to solve the crouching effect, but that's fine. Oh, here's a test. What happens if I walk into the wall while crouching over and over again? What happens? Maybe I should turn on a collider so I can see what's going on here. Very weird. Quite strange. Oh, it's because I'm not colliding with the, okay, it's because it bottoms out. Yeah, okay, so it's bottoming out, which is not ideal. I'm not sure why I'm like, how I'm stable here. Yeah, I don't know what's going on with that. Why am I stable here? Why am I not sliding? This is really weird. Is that... Huh? But then I stand up and I'm not... I'm actually really confused now. That's a really odd thing that's happening. Ah. No, okay, I see it. It thinks I'm on the ground, right? Because it's doing this other collision cast. And my collider would technically be on the ground at that point. Yeah, okay, it's just... It is a bit weird. But it's also not weird at all. Yeah, I'm not sliding down because I'm technically, like, not actually slipping here. Because my thing was to extend, it would be touching the ground still. So if I look at my height, if I do this if I line this crosshair up there, go forward, it doesn't actually go. If I back up, it stays at this height. See? So it's kind of like I'm laying against the wall almost. But then I jump up and now I'm sliding, right? I can crouch. I'm stable. Which I guess can do this. Because yeah, if I back up from the wall, I don't drop. The collider just continues to go down. Okay, yeah, that's not weird at all. Alright. But is it weird? But is it weird? Does it look weird to do that? Yeah, it doesn't... I'm not sure what I saw there. It looked weird, but it's not weird at all. It actually just makes sense. Maybe it was just from the outside. I was like, why am I not moving? Because I thought I should be slipping, but that was my assumption. Being wrong. Alright. I like it. It's all... That all checks out to me. That's really, really good. Not too much changes, right? I have some things where I just fix that. That's kind of a fix. We're not slipping if we're not slipping. Yeah. I mean... I do have this add slip, which I don't think is actually there anymore. That's totally handled now by... I should just be able to take that out because this is totally handled down here at the bottom. Yeah, that was just totally handled elsewhere. Okay. Okay. Yeah, slightly better calculations there. Some fixes to support this. Really light. And then calculate ground forces, slip. That just, yeah, that makes sense where it's at now. Add a slipping force, because I'm multiplied by mass. Mesh you off as well false. Let me undo that. Change. Test world. I have the box that gets flung. Cube, and then the slope wall. And with the play around, I turned all the debug stuff on, so let me turn the debug stuff back off. Because this is pretty much done. Yeah, I'm actually just so glad that I put the debug on there, because that's exactly what I needed. Because I was noticing that really huge green vector appearing while I was jittering, and I'm like, is that the cause? I turn it off, it stops, no more jitter. I'm locked in on the wall. Really happy with it. Okay. At max slope angles, slipping. What was the thing that I changed that needed to be corrected? Let me look at this again. There's a certain line that I changed up here. Yeah, the slope cosine theta I dot with my forward direction, not my ground direction. Yeah, so I need to document that. That's technically a bug. Was a bug, not anymore. Yep. That was actually literally it. Also, fix movement bug related to inclines. When ground velocity it was mistakenly incorrectly using ground direction when it should use forward direction. Incorrect using ground direction when it should use forward direction. Set a max angle to prevent walking up sheer inclines, and modify spring behavior when on floors near walls to stop bouncing jitter. Slide gravity against slope. Slide gravity against slope. I like that. I like that. Okay. Now, it's going to be lunch, and then I can get on to the Spiderbot stuff, which I'll have to figure out how to do that. I'm starting with something that I think is going to be really hard to do on purpose so that I can decide quickly if I need to exclude it from the game, because it's just going to be, it would just be too hard. Perfect timing. I hit pause right before it slammed me. Alright, but this is already nice. I like that I can walk into this and I'm not... It just feels like a wall. It doesn't also feel like... whatever, right? Let me try this thing again. Let me try to run into this thing and see. Oh, and I can actually push it thoroughly too. So that's nice. Because what would happen is if when I hit it dead on, I would stop because I would think I was on a slope, so it would stop. I couldn't push it so easily, but now I can because I ignore that object and I cast it again, and I say, yep, I still have ground right there. We can just stand on that. And I say I'm not slipping, and I just, yeah. Cool, cool, cool. That was a good thing to do. That was a really good thing to put in there. All right. Yep, I'm going to go get food and be back in a minute. Oh, that launched way harder that time. I'm gonna get on this elevator just so there's motion. Okay. I'll be back. I'm back. I see that it says I disconnected and reconnected, so... Okay. I've got food. I'm going to eat. I'll be back. I'm back. Stand time. All right. Robot. Whatever. All right. You should use create a collision area. Yeah. Create a controller today, tomorrow. That's done. It's just literally done. Player, I subtract a new line, or I've added an extra new line? It's an extra. Stiffness frequency slider. Currently, you can jump up walls forever. That's probably just like an is slipping check. But here's the thing. I want you to be able to jump one time when slipping, but not any more than that. I don't know. That's hard to decide. I don't really want to do timers. If you let go of the button, you press it again, and you've landed, you can jump again. I don't think I want to turn off slide or turn off jumping if you're slipping. I still want, like... I don't know, maybe you get one jump. How do I determine that? If you're slipping, you get one jump. Or how about this? When you jump, you're locked out of jumping again until you've landed on flat ground. So if I jump in the air, I can't use a jump to jump onto a bad slope and then jump again. But I could walk into a bad slope without ever having jumped and then jump. So it's kind of like you can store a jump, I guess. You have to be on the ground, but you have to have previously touched flat ground. I could just add that. I could just do that. Could add it. I could add that. I could add that. Oh, no, think about this. I have a Boolean. It's true by default. When I jump, I set it to false. When I land on flat ground, I set it to true. And when I jump, it has to be true before I can jump. That sounds really, really simple, actually. So I'm just going to go with that. There's going to be a Boolean. Can jump from flat. Can jump from ground. Um, right. So it's really simple. I go down here, somewhere around here where the floor stuff is calculated. True. Well, okay. Not exactly that. Okay, those become true there. And then when you jump, this is the commit the jump is on floor, not force ground movement. I guess I just say it just becomes false here. And I've already done ground detection, so I already know that I'm on the ground. Okay. Still jump like normal. And jump up and down stairs. Now I cannot do this. Oh. You get like one jump, right? Actually, that's kind of stupid. Interesting. Because it seems like I'm still colliding with the ground. So even though I've jumped, I still have one additional jump I can make. Maybe that's okay. Right? If I have the idea that you can jump. I mean, it just allows you to jump from a flat ground, and you're still like, there's like one additional frame where you're still pushing off that you still have upward momentum, but your spring extends into the ground and says, oh yeah, we're still on ground. That then allows you to, it resets and says, yeah, you can jump again. Or you can jump from flat ground again because you just touched flat ground. Honestly, I think it's probably fine. This is a small change just to stop jumping up walls infinitely, which it does do that. So I'm honestly not interested in fixing that. I think I'll leave it. You know, it can kind of be like some kind of tech thing where you can use a jump and then you have like a second jump off a steep incline if you, I don't know. I don't know what you would do with that, but Definitely stops, you know, being inside of an area with steep walls and the intentions that you can't leave. But then you just walk up to the wall and just keep jumping up it forever. It stops that. That's really all I cared about doing. And it stops that. You get one jump, but that just means I just have to make sure nothing is high enough that you can do that extra jump and then get over the wall. Which is just testing anyway. Okay. Okay. All right. Now the big stuff. The big thing. How do I make a robot? How will I do this? I mean, I'm just planning, really, is what I should be doing. I need to, this is a big plan. So let's do enemy untitled. I'll call it Spiderbot. I'm gonna go here. I'm going to commit this, but I can remove this little tag. That's stiffness is fine. Well, that's exactly what it is. Stiffness is just that. We'll do git add. Right. It's all in. Okay. Spider. This also ties into thing. Hostile robots. So I've got written down is a crawling spider machine that go on any surface, walls, and ceilings. And I should have the video. I've got to get Where is it? There we go. So this is a good example. So I'll just say moves using the more legs I add, the more complicated it gets. Also, the more legs I add, the more unreasonable it becomes as far as like an actual engineering thing. I mean, really, you probably only need 3 legs to be stable on a wall. I guess I'm just thinking about the configuration. Are they, you know, equally spaced? You know, it's like a square shape. Is it more rectangular? Is it wide or is it long? Is it square shaped but the legs are angled forward and backwards or angled to the side? Does it walk like a crab? Does it have that posture? Do I have an image? Did I have an image for something like this? That looks interesting. There's that. Yeah, so there's like forward or back legs. That's how these kind of both operate. This is a forward leg, this is a back leg. A rover. These are kind of also forward and backwards legs, but this is definitely more square shaped. Small size and generally easy to destroy. I will say yeah, man, I kind of need to plan out the whole thing. Like, how does it attack? I think how small is small, right? Am I saying like the size of your hand small? Because if that's the case, I can almost just, you know, disregard doing what is it? I can almost disregard doing any kind of raycast. I can just have it straight up. It touches something, it'll, you know, it tries to align its forward vector like that. I'm thinking of like a crease, you know? Because the other ones have used raycasting for the motion, which means the raycast goes forward. So if the crease is more extreme than the raycast is, it kind of, it doesn't, you know, you can't walk up that. I guess I could use a lateral raycast if the first one fails. Or just a lateral raycast to like move a leg up. So if it comes up to like a 90-degree angle. Normal raycast could still handle that, but if it's a crease, if it's a sharp crease and it walks into like the corner, it sees this forward raycast hits and it's like, okay, let's move the leg up there now. And now this is our plane, right? So I can walk up creases. That is a solution. There's also this look that I'm not sure if I like. Let me go forward to find it.
Godot 4.0, I've received a few requests to update my tutorial. In this video, I'm going to show you how to create an improved procedurally animated spider
weird
that is fully
rotation
controllable
thing
and
that I'm
can
not
walk
really
on
sure if
rough
I
terrain, walls, and ceilings. The first step.
I guess it just kind of depends on how large you make the legs and how large the object is. You know, then maybe it doesn't look so weird if it's kind of turning ahead of the surface.
Target container, which we'll need for later. To make things quicker, I'm copying the IK target nodes, removing top level and renaming them to step target. We want our step targets to always align with the floor, so I'm then positioning ray cast nodes at the step targets, angling them slightly and moving them up. The angle helps when attempting to walk up 90-degree surfaces. Angling them slightly and moving.
Yeah, I mean, let me put this in slow motion so we can see it. Okay, slow motion's just for some reason not an option. Gotta mute it, otherwise it sounds horrible. Like, the body starts to move before... I mean, I guess it actually doesn't. Never mind. It's actually not moving. It waits until it starts to put its leg on the wall, and then it decides to reorient itself, to rotate itself. But coming down, it does kind of take a while. Whatever. If it's small enough, it probably doesn't. Even if that was happening, it probably doesn't become an issue. I'm just gonna watch this whole video again. I'll crank up the speed though.
With the removal of the skeleton modification stack from Godot 4.0, I've received a few requests to update my tutorial. In this video, I'm going to show you how to create an improved procedurally animated spider bot that is fully controllable and can walk on rough terrain, walls, and ceilings. The first step is to have a model that's been rigged. I'm using this quick one that I threw together in Blender. If you want to follow along with the video, I'll put a download link for the model in the description. Now in Godot, I've created a simple room in the main scene using CSG nodes. I'm now creating an inherited scene from the Blender model and updating the material so it looks a little nicer. Now let's get to the IK setup. As I mentioned in the intro, the skeleton modification stack is removed from 4.0. Either they'll re-add an improved implementation in a later version, or we'll get something new entirely. For now though, we need to use the deprecated skeleton IK 3D node. Add 4 skeleton IK 3D nodes to the skeleton node, one for each leg in our robot.
Let me double check that this still exists. I guess I can just go and start by making... I mean, I guess it's gonna go in character. I meant to do scene. It's actually gonna be a... that. Skeleton IK 3D. Notice to rotate all bones of a skeleton 3D bone chain in a way that places the end bone at a desired 3D position. All bones chain. Yeah. Okay. Wait, what? What is this IK modifier? IK modifier. Settings. Maybe I should be using this then. I mean, it seems like this is exactly the same thing as an IK 3D. I'll look at what Skeleton IK 3D does. I give a root bone, a tip bone, and a target position. Iterations. Skeleton modifier stuff. Use magnet. Deterministic. A target node, a root bone name, and an end bone. I feel like I should just use this. This is not deprecated, this is put in there. And they say it's for biological animals too, or biological whatever. Iterate IK 3D. This is for all joints simultaneously. Biological animals and biological animations. I'm not really sure what that means, but I can just use that. Skeleton node set. Settings with no target set. No target. This doesn't have a magnet though. But I'm assuming iterate, fabric, settings. This will just iterate. This is really cool. And it uses a node instead of a target position. Okay. I'll use that. I should be able to use that. It's not a deprecated thing. It looks like it's the new thing that's meant to be used. I mean, yeah, it says it's not deprecated, so I'm sure that's what I should be using.
There's a strange behaviour where only the bone before the tip bone will point at the target, but in our case we actually want the last bone in the chain to do that. To work around this, I added an extra bone at the end of the bot's legs in Blender that has 0 weighting for mesh deformation, and set that as the tip bone in Godot. The root bone is the third bone up from our tip. We also want to use a magnet force with a value set to 10 on the y-axis to keep our legs pointing upwards. Set this up for each leg. Now let's set up 4 nodes to act as our IK targets. I'm using markers to make them visible in the editor. Adjust their position until you're happy with the default pose. We need to attach a script to our IK nodes to start the IK simulation when the game is started. We can add tool to this script so the IK runs in the editor too, which makes finding the right positions for our targets easier. Get the targets into a place you're happy with. At the moment, if we move the scene's root node, the IK targets will move too. We can set the transform to top level so they will ignore the parent's movement when the game is running. Let's add a script to our robot so we can move around. Attach a script and at the top export 2 variables to hold the move speed and turn speed. Then in process, let's get our input directions and translate and rotate accordingly. You may wonder why I'm using rotate object local instead of rotate Y. Using rotate object local like this means we're always rotating around the object's local Y axis. Regardless, let's add our bot to the main scene and try it out. To handle walking, our IK target is going to track its distance to a step target. Unlike our IK target, this step target node will not be top level, so it will move along with our spider. If the distance gets too far, we'll move our IK target to the step target's position. Let's begin by setting up our step targets. First I'm going to add a node 3D called step target container, which we'll need for later. To make things quicker, I'm copying the IK target nodes, removing top level and renaming them to step target. We want our step targets to always align with the floor, so I'm then positioning raycast nodes at the step targets, angling them slightly and moving them up. The angle helps when attempting to walk up 90-degree surfaces. To position our step targets to the floor, create a new script and attach it to the rays. Get a reference to our step target node, and then in the physics process, if a hit point is found, move the target position to the hit location. Then, in the editor, set the step target references. Now attach a script to our IK targets. This script will handle animating the target. At the top, add 2 variables. One is a reference to our step target node, and the other is our distance before taking a step. Then, add a new function called step. Like before, we're going to use tweening to animate the target. This is a tweening logic from the old implementation. It was overly complicated and only lifted the leg upwards globally on the y-axis, which ruins the effect when you're walking up vertical inclines or upside down. I've now simplified the tween to this. We get our target position and then find the halfway point between it and our current location. Then we tween to the halfway point plus our owners, which is the spider bot's basis.y. This will be 1 meter up in whichever direction the spider is currently oriented. Once we reach the target, we then tween to the final target position. Finally, in process, check the distance between the target and our current position, and if we exceed our required value, call step. Let's see how that looks. Well, it works, but all our legs are stepping at the same time. Let's make it so we can't step if the adjacent leg on the left or right is already stepping. Back in our script, add a reference to our adjacent leg and a boolean to track if we're currently in the stepping state. Then add to our if statement to only step if 1, we aren't already stepping, and 2, if the adjacent leg isn't stepping. Then, in the step function, set is stepping to true. Then let's add a callback tween to the end of our tween queue. For the callback, we're going to use a lambda function to set is stepping back to false after the step is complete. Set the adjacent references and let's take another look. That's much better. But personally, I like it when the legs diagonally step at the same time. If you want to implement that too, let's add another reference to our diagonally opposite leg, and then when we call step on the opposite leg too. Much better. This looks great while turning around, but while we're walking, the legs lag behind a bit. Let's fix that now. Add a new script to our step container. Add a variable to the top and store our desired offset when moving. Let's also grab a reference to our parent.
There's way too many scripts, by the way. I didn't notice that. He has a script
then,
on
in process,
everything.
We can calculate the velocity by subtracting the previous position from our parent's current position. We can then set our container's position using this velocity multiplied by our offset. Finally, update the previous position variable. This is looking way better. We just need to get our body moving and rotating based on the leg positions now. Back in looking way
Let me pay attention to what he does here.
Much better. This looks great while turning around, but while we're walking, the legs lag behind a bit. Let's fix that now. Add a new script to our step container. Add a variable to the top and store our desired offset when moving. Let's also grab a reference to our parent node and store the parent's previous position. Then, in process, we can calculate the velocity by subtracting the previous position from our parent's current position. We can then set our component's position using this velocity.
Yeah, so the problem I see with that is you're teleporting your targets, right? So if you're already near a wall and you press the button, that teleport can essentially just causes it to be not continuous. Yeah, so a lot of this is good, at least for like how you might set up in Godot. But I think most of the logic that I'm going to use is from this version that someone has in Minecraft, which isn't even on the side.
Finally,
but it should be.
update the previous position variable.
I'm going to go look at that.
This is looking way better. We just need to get our body moving and rotating
That's definitely
based on the
going
leg
to be
positions now. Back in our main Spiderbot script, let's first move our movement logic into another function for neatness. Then, let's add some references to the top to hold our legs IK targets. Let's also create a variable
gate
to hold our
stuff,
side
and
height
like legs
offset
are
from the
pretty
ground.
generic.
In the old video, I
used
used
to
the
seem like
following logic to handle the rotation, taking the average leg positions and using the difference to calculate.
I don't need generic either. I'm gonna have 4 legs. I mean, technically this could be used. I guess I could make this generic, such that I can attach this onto a 2-leg robot, and not necessarily walking up walls, but use that at least for that procedural walk thing. However, kind of an unfortunate part for that is I would like to still have animation control, because otherwise I have to go in there and have to like script up the animation to look how I want it. But also it's a robot, right? It's going to move according to an algorithm. So it's going to be very precise. Things to think about.
Calculate rotations on the relevant axis. This method works great until you go upside down or vertical, and then it quickly falls apart. I had to come up with a solution that would work for any orientation, and that's when I remembered my old friend the plane class. A plane is essentially a position and a direction, also known as a normal, that has various uses. One way we can initialize a plane is by putting in 3 positions in a clockwise order. My idea was to create 2 planes from the IK target positions, then we can average the normal to get our body's desired orientation. We just then need to be able to turn this normal into a transformation basis. We can do this in a similar way to how we did it in the path-based mesh generation video. I'll skip the explanation on bases as I already went over it in that video. Our new basis, y, is the normal direction. Its x is a normal crossed with our forward direction, and the
normal cross our forward. Yeah, I mean, that gets you the right. Orthonormalize. I don't know what the point of multiplying it by the scale is, but whatever.
z.
Yeah, multiplying by the scale is kind of... I mean, I guess it's good, it's smart to use that, but not
is the right direction crossed with the normal direction. Finally, let's overwrite our basis with the newly calculated one. We can use lerp2 to make this smoother. Now let's check the results. Awesome, we're almost there. There's just one last thing we need to do. We need to make sure we lift the body up and down based on the height of the IK targets. Let's calculate the average position of the legs, then calculate the target position as this average plus our bot's up direction multiplied by the ground offset. Now we only care about the distance between our current position and the target position in the spider bot's current up direction. We can calculate this by using the always helpful dot product. If we take our direction, call the dot function and pass in the target position minus our current position, we'll get only the difference for that direction. We can then lerp towards our position plus our up direction multiplied by our calculated distance. This will work no matter which way our spider bot is oriented. And there we have the final result. There's a few things you could do to improve this, but I'll leave that up to your imagination. Anyway, I think that about does it for this video. I hope you found it useful. I'll leave a GitHub link to the finished project in the description below. If you found this video useful, please give it a like and think about subscribing. In the future, if a Godot update has killed this implementation again, let me know and I'll do another updated video. I've recently started streaming my Godot tinkering. Recently,
Whoops.
Valve announced Counter-Strike 2
Nope.
in raycast nodes.
Okay, so some good stuff there. But I've got to go look at this other one now. To I just realized after I typed, I'm like, that's not going to give me what I'm looking for. It did, actually. It did give me what I'm looking for. And he's got 3 videos. They go through a lot of things. So I mean, I'm just gonna watch all these. I'm just gonna load them all up. But I can go through this at a bit faster speed. Do I have that? I add it. Previous work. Let me get that. um, and then this, oh geez, where am I going? And then this. I guess I should just make a playlist. Save. Um, cool. Just okay. I wanted it just gave me the link as the thing that I can click, but just gonna do that. It's actually all written in Kotlin, so I'll note that. And I'm gonna watch through all of them. I'm gonna watch through them all.
Hi, today's project is a spider with a procedural walking animation. Its movements are generated in real time to adapt to its surroundings, which would be infeasible to implement with traditional keyframed animations. Let's start by creating a kinematic chain for a lake. A chain is composed of a root node and any number of rigid segments, which we can render using the new block display entities. To move the chain, we will first move the last segment to the target position. Then, we will recursively move each parent segment to the base of its child. Now the chain is no longer attached to its root. We can move it back using the same principles. We will repeat this procedure until we find a solution within some acceptable margin of error. This is a commonly used algorithm called fabric. Currently, the joints can rotate with 360 degrees of freedom. This is fine for flexible appendages, but for lake joints, we typically want to restrict them to only rotate on one axis. To apply this constraint, I straightened the chain towards the target before applying the algorithm. Here, I created a spider with 4 chains for lakes. Let's accelerate the body forward. If each lake gets too far away from its rest position, let's tell it to return to the rest position. Let's also make sure that the adjacent lakes are grounded before we start moving each lake. Right now, the spider will stand in awkward poses after coming to a rest. Let's decrease the trigger distance while the spider is standing still. One other issue is that the legs will phase through each other if the rotation changes too rapidly. We can interpolate the rotation gradually across multiple frames. Next, we could tell the spider to stop moving if its legs get too far away from their rest position. Right now, the spider can only walk on a flat plane. To fix this, we can scan a column of blocks to find the ground height and use that as our new rest position. We need to move the body as well, so I averaged the position of all the legs, added a small offset, and used the result for the body position. Next, I would like the spider to respond to gravity. To add this, we will accelerate the body downwards. If the spider has at least one pair of opposite legs on the ground, we can apply an upwards force to counteract gravity. For the final challenge, I want the spider to be able to walk on these discontiguous pillars. This is impossible with our current strategy, as the spider's legs won't be able to locate the ground while passing between gaps in the terrain. To fix this, we could try scanning the 8 neighboring columns as well and picking the one closest to the rest position. However, this created a new problem, since the legs would now prefer moving half a block to the adjacent columns instead of stepping up one full block. To address this, I set the comparison point half a block above the rest position if the path is obstructed. Lastly, I want to mention a bit about the block design.
That part of it is easier to do in Minecraft because you can just say, all right, the neighboring blocks, right? What would that look like in not Minecraft? Perhaps I would just have a larger radius, and it says, all right, look for, maybe not even a larger radius, but like scanning forward ahead of the robot. So if it wants to move forward, it has its target position being a circle, or its target region being a circle. And I mean, I can also just make them smaller and also just not have that. That's a possibility. I could just not have that. They would not be large enough to scale such a significant gap. Locally to them, they either have, I don't know, or maybe I should make sure I do that. So they can scan ahead a little bit. So if I do have any small gaps in terrain, or like there's a crate or something and they're walking from a wall onto a crate, there's a small gap, they should be able to move. Okay, that's kind of a crazy thing, actually. That's probably not. Yeah, I don't know.
Display entities
Something to think
are
about.
used to render the spider. In Minecraft, all entities can rotate onto axes. They have a pitch, a yaw, but no tilt. This is a problem for the leg joints, since every time they cross over the y-axis,
I think I can skip the rest of this. That's just not... The hell? That's not what I put in the queue. How did I mess that up? Wait. No. No. No, 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 that's not correct. It's not supposed to be in this playlist. That was dumb. Okay.
Hi, this is a follow-up to my last video about procedural walking animations. Since then, I've added support for different body plans. Here's a really small spider, and here's a really big one. Here's a quadruped, a hexapod, and an octopod. They all work using the same rule sets I described in the last video. All I had to do was generalize the functions I used to group adjacent and diagonal leg pairs. I've made a few improvements to the rule set. The legs now move ahead of the rest position. I also added an adjustable cooldown to space position. I've made a few improvements to the rule set to group adjacent.
I see the
and diagonal
interpolation
leg
here, though.
pairs.
So you can see them. It's really, it happens really fast, but they shift forward.
I've made a few improvements to the
Instead
rule
of
set.
teleporting instantly.
The legs now move ahead of the rest position. I also added an adjustable cooldown to space out the movement of diagonal leg pairs. Next, I added galloping. While galloping, we group legs into horizontal pairs. A leg in each pair is designated as the dominant leg. When the dominant leg exits the trigger threshold, we will move both legs at the same time. We can add a cooldown between vertical pairs to prevent that leapfrogging motion. We can also customize the gait by adding a cooldown between horizontal pairs. Unfortunately, this does not play well with our current gravity system. In the last video, we apply a normal force only when there is at least one ground diagonal leg pair, but this is too big of a simplification to support galloping. So I came up with a more elaborate rule set that doesn't require a full rigid body simulation. The first step is to specify a center of mass. It does not need to be accurate as long as it's in a believable position. Next, we will draw a polygon around each grounded leg. If the center of mass is contained within the polygon, we apply an equal but opposite force to gravity. Otherwise, we apply the force at an angle originating from the closest point on the polygon. To detect if a point is contained in a polygon, we will cast a line from the point towards an arbitrary
Crazy
direction.
shot.
If there is an odd number of intersections, then we know it is contained in the polygon.
Just looks like a spider on the screen.
An unintended benefit of this new system is that the spider now falls off ledges in a much more convincing manner. I also added cloaking. Each segment locates a block in the player's line of sight and camouflages itself by adopting a similar texture. However, it does not copy the block directly. For one, it avoids switching to blocks with directional textures. As an example, grass blocks are mapped to moss blocks. For another, it avoids transparent or non-full blocks. Leaves are mapped to moss blocks, while slabs and stairs are mapped to their full block counterparts. I thought the camouflage pattern worked too well. To add a bit of imperfection, I made it intermittently select a block with a similar color. The randomizer is seeded with the segment's position, that way it still looks random without being too chaotic. For the glitch effect, I used glazed terracotta. To address some of the questions I got in my last video, here's a more detailed visualization of my inverse kinematics implementation. A chain is composed of a root position and any number of segments, each containing a length and a tip position. To move the chain to a new position, we first set the last segment position to the target. Then we will subtract the parent position from the child. This will give us a vector indicated by this arrow. Next, we will normalize the vector. We will divide it by its own length, resulting in a new vector with a length of 1. Finally, we will multiply the vector by the segment length. This vector now represents the segment space position, which we can use as the target for the next segment. We will move the chain back and forth until we find a solution within some acceptable margin of error.
Skip this.
Hi, welcome to the third video in my procedural animations series. I finally decided to give the spider a proper body. Staying true to my goal to not use resource packs, I designed 3 torso variants using only block display entities and vanilla assets. There's a flat variant, a boxy variant, and a militaristic or stealth variant. Of course, you can further customize the designs by changing the block palette, size, and body plan. One unusual way to customize the model is to change the brightness of the display entities. The default value is 15, but you can lower it all the way to 0 for pitch black. In fact, I used this for the stealth variant because at first, when I used black concrete, all the shape details blended together due to how dark the texture was. To fix this, I used grey concrete instead and then lowered its brightness. Using the same idea, I darkened the other textures in the lake models. I also completely overhauled the cloak system. I wrote a script to crawl the Minecraft assets folder and generate a list of blocks with their average color. Using this list, the cloak can look up the color for any block, and likewise display any color by finding the closest match in the list. This allows me to interpolate the color value to create a smooth transition effect, similar to what I did in my 3D renderer video. Using the brightness option, I was able to further increase the number of available colors by generating 15 darker shades for each block. Previously, I managed to make the lake segments bend in the same direction by reinitializing the chain every time I applied the fabric algorithm. However, in the new lake designs, one of the segments bends differently from the rest. To support this, I added an initial rotation parameter for each segment, so I could have some control over how the chain resolves. Of course, this is still just a shortcut with many limitations, so we may want to implement a proper constraint system in the future. Now that the spider has a visible body, it looks odd that it can only rotate on one axis. To support 3 degrees of rotation, I rewrote the plugin using quaternions, as they tend to be easier to work with than Euler angles. To calculate the target orientation, I take the vector between the front and back legs and use it to calculate the pitch. Likewise, I take the vector between the left and right pairs and use that for the roll. I give the spider about 30 degrees of leeway so it can look at the player or at the laser. I considered rotating the scan bars as well so it could scale steep terrain, but this feature still needs quite a bit more work. I've disabled it in the meantime, but you can re-enable it in the settings if you want to try it out.
Yeah, it just looks like gravity. Oh my gosh.
Next, I wanted the spider's body to rotate when struck by a trident, so I implemented angular velocity. In the process of adding this feature, I accidentally created a subtle spring effect when the spider rotates. I decided to keep it, and you can exaggerate or dampen the effect by tuning the parameters. Since version 1.21.3, it has been possible for servers to receive user input directly. Using this feature, I was finally able to support keyboard controls. This was something I wanted to do in the past using horses, but there were too many problems in making it work reliably.
Alright. Pretty much it. I do like the 6 legs, though. Seeing 6 legs versus 4, I like that more. It is true that all the source code for this is just available as well. So I don't really have to assuming none of that's really there. We have this. One sec. Ooh, I am kind of running out of time. Set up spider body. Huh? Right, it uses this entity component system, which replace component spider behavior. Grab all entities that are spider bodies and replace the spider behavior component with a stay still behavior. I guess. Resets. Balance. Leg models. Okay. Model stuff. The body plan. Add a leg pair. A biped add one leg pair. Leg plan. Segment count. All right. Equal length. What? Oh, equal length. To the list of segment counts. I guess it just duplicates that. Yeah. With the length and a forward vector. Okay. Options. All right. Yeah, this is very generic. Ugh. Walk gait, gallop gait. What? Oh, default walk. Default gallop. Apply. There's a lot of stuff here. There are so many things here. Stay still, target direction. What? Dude, what is Colin? Hang on, what am I looking at? App. Function spider body dot rotate towards. What? What is Colin? You can just write that? Surely not. She can't just write that. I'll be right back. I'm back. Okay. There's also stuff about the legs being on the ground or not, which I guess makes sense. Legs in polygonal order. Lefts, rights, lefts plus rights reversed. Did hit collision offset the length. Effector straight down. At least a meter or whatever its velocity is. Position velocity wise less than 0, which means it's going down. Dampen the Y velocity by the bounce factor. Velocity is less than the gravity acceleration of the gate. 0. Okay. Those look like just some hacks. Calculate preferred. I didn't see these legs in polygonal order or anything. This is just pretty typical. It does do legs update. It does this get legs in update order, which probably, wait, what? Is that gate type? No, it's gotta be an enum. Where was it? I lost it. Get legs and update order. Gate.type. Okay, so it is like gate.type. Legs and update order. Legs is spider legs. Indices filter diagonal 1 is diagonal 1. What? Indices map. Spider legs. Okay. Walk gates, get legs in update order, update order. Okay. Can move leg. Spider leg, the index of the leg. Always move if the target is not on the ground. If the target is not grounded, we are trying to move the leg. What does move mean? What does move mean? I guess it means if it's supposed to be off the ground, then you're wanting to. I guess that makes sense. It's a weird way to say it, though. We consider leg to be primary. Crosspair unindexed leg. Sure, other pair is grounded. Adjacent to this one. You're getting the pair that is unindexed leg. Map or null. And that just seems kind of ridiculous, to be honest. It just looks ridiculous. I don't know why you would have a function for that. Yeah, I don't, that's just kind of, that's a bit weird. But sure, why not? The other pair is grounded. If any pair is not grounded and is not disabled, and its target is grounded, that's rude. Essentially, this is just asking the question, is the other leg moving? Weird. I don't know. Cross pair. Oh no, I get it. This is to leg lookup grabs all adjacent legs. So this is all legs adjacent to this one. Like look, that's all legs which are diagonal to that one, which I don't even know what that means. I don't know how you generalize that. That should, whatever. Same pair is just checking the other leg. If that leg is grounded and or its target is grounded and time since begin move is less than its cooldown, falls, wants to move, leg is outside trigger zone, or the leg is not touching the ground, hit target, and effector. Distance squared is less than that. Oh yeah, they do distance squared. On ground, if any of the legs are grounded, or the spider is on the ground, I don't know why I wouldn't just check that one first, since it's a single lookup instead of checking all legs. Whatever. It wants to move. It is not already at its target. Leg is outside trigger zone and leg is not touching the leg is not touching the ground. This is really strange. Is grounded and touching ground just the same thing? Why make a function for that? Okay, well I think I've looked at that plenty enough. Let's see leg. I want to see what is grounded is. Touching ground, not moving, not disabled. Okay. That's not correct, actually. Is grounded should probably just not be a function there. The function should say is grounded and not moving and enabled is probably what I should say. Also, I hit the negative stuff too. Having a toggle to disable something is wrong. It should be a toggle that it says enabled. Enabled is false or enabled is true. Instead of saying is disabled is false. We are not disabled, which means we are enabled. It should say, are we enabled? Yeah, don't name booleans after a negative. If you're using a negative in the name of a boolean, then invert that. I know there's been some stuff somewhere where it's like, hey, every time you use this boolean, you're inverting it. Maybe you should just not invert it anymore and invert the name. Don't do that. Just if it's use the positive for a boolean name and don't care if you always negate it. It doesn't matter. If it reads like English, then that's what you want. Is uncomfortable. That's funny. Is uncomfortable. I guess update memo is just to do some stuff before you save all your data before anything starts moving. Should probably just be like pre-update. Probably what it should be called. Update memo is a fine name too, because they both start with update. A lot of this quaternion stuff, I don't really have to worry about that. The basis is essentially a quaternion. I mean, I'm just thinking about animation versus this, because this one does say biological animations. So my thinking is the IK has... Wait, where'd it go? Why'd I delete it? Bring it back. Deterministic is what I saw. The previous frames IK 3D result as the initial state. From the bone pose excluding the IK. So I guess this means I'd like use the animation as like, or the bone's rest state, so I'd have to set up the rest pose to be the pose that I want the legs to kind of fit to. I don't think I can create skeletons either. I think the only way to get that is to import one. Let me just see. Yeah, I can't just make one. Right. Alright, what would I want it to look like? Also, I really like the 6 legs. I really like 6 legs. I might have to do the 6 legs. Because 4 just doesn't seem like spider enough. But 6 is. But 8 I think is too much. 8's too much. But it does matter how big I want it to be. If it's going to be small, then only 4 legs makes sense. If it's going to be larger than that, then 6 legs would make sense. But if I'm going to have it have 6 legs, if I'm going to have it with 6 legs, then I may want to make it generic a little bit, using up their leg lookup stuff. I'm also feeling kind of tired right now. Feeling pretty tired. I can't decide. All right, in the game, what do I want to see? What do I want to see happen? I walk into the room, it's dark, and like lights come on, or all their eyes light up, and you see all these spiders on the walls. How big are they? How many legs do they have? I feel like I need two. Honestly, I just want both. I can't decide. Why not have both? Right? I can have small 4-leg ones and larger 6-leg ones. And then it could even be like the mom spider and the children, right? A lot of small ones and a couple big ones. A hierarchy. Hierarchy definitely makes it more interesting, right? If you were to see that, you know, the question is, what do you start with? You know, I think typically you start with the smaller ones because they can deal damage to you. So, and you can get rid of them really quickly. So you get rid of, you know, 20 of them in a single burst or whatever. And then you start working on the big one, right? Or you can do the big one first. I don't know. You can pick. It's a decision to make. Oh. Big one. The larger spider will have 6 legs in a... Well, 6 legs and a long body. It is probably armored. It is probably armored. Little one. Smaller spider will have 4 legs with a round body. Not armored. Very fragile. Should appear in 2 sizes. In 2 sizes. I'm just thinking this is gonna be a scaled. 2 scales. Let me think about this. Ruler. Measuring tape. Where's the meter? There's a meter. So I think the big one's probably a meter tall. The small one, maybe go like 60 centimeters. Or the medium one's like 60 centimeters. A bit over 1 meter in standing height. And about 50 to 60 centimeters. Probably I'm thinking like, it's gotta be small, right? But you know, big enough to put equipment on. So probably like 20 to 30 centimeters maybe. 25 centimeters. I'll say 25. Figure it out from there. Serpent spiders like zombie spiders. Robot spiders. Okay. So what do I need to do? What needs to be done? Need? Yeah, definitely a general leg support system. Handles missing legs and walking with or walking with an, I'll just say arbitrary number of pairs. I'm wondering what I do with the spring, because I can't just turn off the spring. I can set up the character controller so it just ignores that, and I can use some, I don't know, there's things about this that I need to think about. How do I connect the character controller to something like a spider? Ultimately, I'm just giving the character controller the direction I want to move in, how fast I want to go, slope effects, if I want to jump or not. And there's other tune parameters like slope, angle, and stuff. Acceleration, deceleration. That's what I give it. And it does also, I mean, I guess if I was doing IK where I have raycast and I produce a plane from that, I can say, all right, I want my forward vector to be, you know, perpendicular to that plane. So when the plane starts moving up because it's near the wall, the forward vector goes up as well. So forward just becomes relative to the bot. The question is how, I'm still not even thinking about how that would even work for, how does it know when it wants to go on a wall? Making a mother robot spider when you kill it, a million spider babies? No, I don't think so. They're not going to be like that. It's not going to be spiders, but they're robots. It's going to be robots that were made in this way. So unless it makes sense to like create a robot like this, then I'm not. There could be a reason. You know, terrain traversal. Wheels can't go up walls. You need really big wheels to go over, like, super rough terrain, or just tracks. You can't have a small thing go over, you know, a huge boulder. Reason is nightmare fuel? Nope. My thought of like stuff being scary is that it should be scary because it's dangerous, not because I made it look scary or I just made it freaky. Also, I don't have to worry about that because spiders are already, they already look freaky to us. That's baked in. How does it know when it wants to walk up a wall? How does it pathfind on walls? How would I tell it, here's the player, but you should walk up the wall? So like if I put you in a hallway and there's like 10 of these robots, some of them should decide to go up on the wall. What makes them want to do that? I don't know. I don't know. That's not a question I'm trying to answer right now either. I just know that if I give the controller the right forward vector and I do things like gravity, yeah, I couldn't really have a spring. I'd use AI for coding. I don't. I've heard it's very useful. I think it only slows you down, honestly. If you've never written code before and you want to like have it as an assistant, sure, but it's like training wheels. At some point you need to take them off. Pretty much everyone that I've seen who's used it long enough eventually says, I regret having used it so long and I wish I turned it off. Because it's just like, it's been like damaging to them. You'll just like stare at the screen and like forget how to write a for loop or something because you've let it autocomplete so many times. Or it just gives you the wrong answer and you just accept it, and now later on you end up with a bug and you struggle to track it down because all the code looks correct. Or it's just code you've never written before. That's the problem. Never written before? That's a weird way to say it. Code you didn't write is a problem. I've gotten a bit sidetracked. So handles any wait. Handles missing legs and walking with an arbitrary number of pairs. Leg pairs. I mean, let me look at this. What would I have to turn off to... Jumping is fine. Everything should be set up for local vectors, local orientations. There's no global. Let me just literally search the word global, because I think I probably have some places that are left over. Yeah, I'm gonna go and fix that. State. Origin. All right, copy this. Shape cast global. Well, that is the one that I need to use. Do I have position? I don't use rotation, do I? I don't know why I would. Basis. It's all from state. I need to go and send that before I continue. Use state transform. It's not pushing? Okay. One sec. Okay. Stable ground movement. Slip is relative to its basis. So it's all there. Let me check that ground. Ground normal is the actual normal of the ground. Yeah, but it should also be considered. Yeah, see, okay, so we dot the ground normal with R up. So if I am oriented sideways and that's ground, right? That's fine. I wouldn't slip. Yeah, how does gravity work if it goes up things? I would prefer if I could work this into use as much from character controller unchanged. Preferably I just say change nothing, but adding like some booleans like enable gravity and then I just don't add gravity or something like that. Enable spring and then I don't do the spring. I can also do I also wonder if I would like to have I could have some call in between here that's like, hey, I've done all my calculations. This is what I think you want to do. Like confirm or deny that or something. Like, I could add gravity. I don't want to get too complicated. I could get really complicated and simulate forces per leg and be like, okay, this leg can apply this much force in this direction. But then I have to make sure that when I'm on the wall, the leg is like, has a force pushing the body into the wall and also acting against gravity with some amount. If you're upside down, it's just the same thing. You're applying a force to stay on the wall and oppose gravity. But I think what I probably say is just, hey, like, I can pretend to show gravity by having the body droop a little bit in the direction of gravity. So, and then only apply gravitational forces if all of its legs come off the ground. and probably do some kind of like, here's also the question, how do I rotate the body? Because the collider is going to have to rotate 100%. Maybe not necessarily, actually. I could just have, I don't know. I could make the collider for the physical environment just be a sphere in the center. And then, you know, the sphere does any rotation of a sphere is the same thing. So I don't have to rotate it. I would just spin like a torso mesh, and then that parent node contains all of the raycasting collision stuff for the legs. Rotation is difficult for a rigid body. It's one thing to just say, you know, pure collision physics, an impact happens, apply a force on this position, and that adds some linear velocity and it adds some rotational velocity. But it's a different thing entirely to say, all right, I want you to turn now I want you to orient to this vector. You know, how do you apply forces to reach that point? And in what direction, right? Let's say my forward vector is here and I suddenly say, align yourself to this vector. You know, how do I interpolate there? What if I'm here and I say, let's go upside down now? Is it just a smooth? Is it always just an interpolation from here to there? Also, you know, the right vector changes, right? Is this now my right vector? Yeah, here's a question. So here's my up vector, my forward, and I guess this is my left because I'm using my other hand, but I say my other hand. I'm using my right hand, which is correct, but whatever. Let's say I say, here's my current basis, here's my new one, right? How do I spin from there? Do I go upside down and then it's like a roll? Is it, I don't know, is it like, there's a spherical interpolation, so that handles it, but I guess in my mind I'm thinking, if I teleport it, I have to give it a forward and an up and a right. I can't give it anything less than that. If I don't, I mean, I can give it an up and a forward. You can deduce right from that, but I don't know. I might be overthinking it. Because it needs to be able to go upside down. It also needs to be able to go into a crease and attach to that. So if I have like a wall at 45 degrees, it should be able to go up to that crease and climb it just fine. I guess that's something I should write down then. Capable of walking into creases greater than 90 degree between floor and wall. And I've been thinking this probably needs a front raycast test to detect approaching wall surfaces. So the normal raycast would be forward, angled forward slightly and ahead. But then I have just a straightforward raycast. Maybe it goes down a little bit. Just to spot walls that are coming in sharp or something that the normal one can't hit. I mean, if it's too sharp, then this one will hit the top of it before it hits that. But I also want to have that one, if it's like a really large crease, that raycast is pretty much going to hit the back face and just ignore it. But then I still have the front one that's going to detect that and say, all right, let's go up here. Getting lasered. Okay. Ready the front raycast. What's the problem here? 50 to 60 centimeters fine, but 20 to 30 centimeters not okay. All right, sure. I mean, I can still use the sphere cast for the body offset, but I just have to rotate. The whole body needs to torque or rotate. So I need a whole body rotation. Can provide a target orientation, and the body will rotate using angular forces. Some bounce is desired, but should be minimal. So if I say from here to here, it'll rotate up and overshoot a little bit, but then correct, and stabilize. I guess I could treat that like a spring, I say if we're some distance away, I mean, I could just do that. I think it's probably what would make sense. Use a spring simulation with damping based on its velocity. So take its total angular velocity as damping, and I compute I don't even know. I actually don't even know how I do that. Yeah, I've actually got no clue how I would do that. One sec. Dog's barking. back. That one bothers me the most. I don't know how to do that. The launcher stuff is kind of simple because I'm just moving it in a single axis. And then when I overshoot, I just snap. But honestly, that shouldn't be done. It should be like a really powerful spring to move it back, like on the next step, right? Like I compute the difference and then set that as my linear velocity, so that after a single step, it will snap, or it'll essentially move back with a really high force. So anything in the way will get knocked out of the way, but if it's close, it's a very small change in velocity. Something for gravity. So is counteract one word like that? I guess it is. They will counteract gravity. Possibly depending on legs. On grounded legs. I don't need to get too complicated. The Minecraft one uses a polygon produced from the legs and then checks if a ray drawn straight down from the center of mass intersects a polygon. And then if it doesn't, it does some kind of, I don't know what math it does to determine a new vector. And that vector essentially becomes an upward force that it can apply in. Or that point becomes the upward push to counteract gravity. The one there is it fell apart when it scales a vertical wall. So it seems like it's probably just an orientation thing where they just did the math wrong. I did see a lot of global Y, or like position.y being used, so it's probably not smart. Velocity.y. You want to take its velocity mapped to its orientation. Position mapped to its orientation. Like that. I need to put something in future to-dos as well here. This is just literally a rewrite. Rewrite stopping friction. It has some problems and seems to break down in a lot of edge cases. Must handle arbitrary orientations and slopes. Most likely use local up relative to ground up. stopping along ground directions. Am I going to understand what this means later? Most likely use a local up velocity scaled in relation to ground up and ground direction and ground lateral velocity and local velocity. Or something like that. I hope you know what I mean. Yeah, that's a big thing. So many disable counter-gravity, possibly hanging on grounded legs. An overcomplicated. Alright, that just is a word. That just is a word. Overcomplicated solution is to. I need to scroll down because I keep reading that my camera blocks this. Overcomplicated solution is to draw a plane using the grounded legs, intersect a ray from the center of mass towards the nearest position of polygon. And applying an upward resistance rotational resistance at that intersection point, allowing the body to rotate I mean, I guess it could also resist rotation by, instead of applying straight up, it'll apply it towards the center of mass, but using the scale of gravity, so it'll move forward, but it'll also, I mean, it should droop. I mean, it would just move, right? It would just move. And it would start accelerating, and as it would have to move its legs to keep under itself. But if its legs were locked, it would just kind of fall over. No global orientations. Can handle going up walls and be upside down. What happens if it's upside down? That's a good question. What happens if it's upside down? It should be able to right itself. So I guess it just checks for collisions if its legs are not on the ground. Or I guess, yeah, if its legs can't reach any ground, then what does that even mean? It definitely means that the ray position that I cast the legs, the target for the legs for, needs to be below the center of the body's plane. So that if it's upside down and is laying on his back, it's not telling it, oh, you have a hit over here on the other side of the floor, right? It needs to be able to say, yeah, there's nothing above me to grab onto. I mean, in theory, I should be able to stick it to a box and fling and rotate the box, and it should stay stuck on the box as well. That's a big thing. It should be able to do that. Of course, it would have limits to its own forces, so it has a limit to how much it can press itself into the ground. It has a limit to how much... I mean, pretty much just that. How much it can press itself into the ground. So if it's rotating, it has a high velocity after that rotation step to go away from the box. So it pretty much should just treat that as, here's my ground, here's my, gravity pulling me away, as if it was upside down on a unmoving wall, right? Like I should be able to stick it on a box, and it should be able to hold onto the box really, really well. I can already see the test for it. I take a cube, I stick a camera to it, I put the robot on there, and then I have the cube like launch or something, like using like being slightly pressed onto a launcher. So the camera should stay stuck on the box, and the whole world behind the box moves. And I would just see the bot, wiggle back and forth or whatever it would do as the orientation is changing and its forces are being applied to it. And then if it's strong enough, it can lose grip. And at that point, that probably is a case where I need to have each leg have a force applied to it. Because if a single leg detaches, then the overall force it can apply drops by that amount, right? It can hold onto a box with 6 legs. It could not hold onto a box with 1 leg, right? Maybe it can barely hold on with 6, and some momentum angular thing occurs while it's in the box that just is too much for one of the legs in particular to handle. So rather than having all legs detached simultaneously, I would just say each leg has its limit, and once that limit is exceeded, the leg just comes off the box and it's no longer attached. So then the total force I can press into the box is lost. So now all the other legs lift up slightly, and this leg probably still can't reach. It would like peel off, right? Is how it would look. I don't need it to be able to do that though. I think that'd be cool. I think to do this properly, that may just be a result. If I wanted to crawl up arbitrary surfaces and apply grounding forces it needs to be based on each leg, applying its own grounding force. Okay, so how would that even work? Because if I just have a rigid body and the whole rigid body wants to move somewhere, then I guess I check, hey, were we grounded the last frame? Okay, we were. Here's our new grounding force. But each leg... I mean, that's the case where I translate it down, or I do the ray cast and I check how far have you moved for each leg. The nodes would have to be simulated too. I would have to actually simulate the nodes as being physics objects on their own. So every step, that target node wants to droop down a bit. Like if it's stuck to the ceiling, every step gravity pulls that node off the ground, or down, away from its previous location. And I say, all right, how far away are we? Okay, well, we can apply this much force. So we apply that force and move it back. Or we don't apply the force. We just say, all right, here's your new velocity for the next step to try and stay on that. And then I say, on the next step, I check where it ended up. And then I can say, all right, well, we applied that force. It actually detached. Or it wasn't on there anymore. So now we can't apply force to compensate for gravity anymore on that leg. I mean, the leg still gets, to move. I mean, I guess I could just do like a ray cast from each leg point. It would say, all right, where are you now? Where was your target last time? All right, ray cast to that. And then if I hit that in a certain distance, then I say, all right, we're going to be able to stay grounded this time. So just, put the leg back there or keep on that target. If it's too far away, then I say, all right, my target's moved away and now I'm not grounded anymore. But each target does have to be like, do I have to set it up as like a rigid body thing with joints? Could I even do that? Like a rigid body with rigid bodies inside? What does that even mean? What even happens if I do that? Let me go here. What happens if I make a rigid body with a rigid body like nested inside of it? What happens? I'm assuming they don't care. They always act like they're top level or something. But there is that. Let me see. Yeah, just nested two. And what if it's over here? What happens? Just move them off the ground so I can see them hit the ground. Whoops. Okay. Interesting. Oh, the other one that doesn't have that. Right. Wait, I did both of them. Yeah, I did both of them. I'm confused. Yeah, one of them was falling faster than the other. Why are they behaving like this? This is really weird. So I kick one. Yeah, it's a really weird thing happens there. Alright, alright. Something really weird happens there. That's just strange. Yeah, one of them was falling faster than the other because its transform is moving based on the other one's transform. Okay. What if I allow bounce? I don't know how bounce works, but I'm assuming it will just make it reflect its velocity off the impact point. Yeah, like that. Like that. Also, I'd probably make these a bit larger than that. I don't know what the size of, like... like a ball for playing a game with really is in centimeters. I can kick it really well. Yeah, I don't know where that went. Why? How am I pressing it like that, by the way? That's like really weird. How am I pressing it like that? It's kind of crazy. Am I moving? Yeah. Yeah, that's just crazy. That's just crazy what happens there. I'm not really sure why that happens. That it is gone. Okay. I mean, probably just like I'd probably just do like, you know, some damping. That'd probably help it from exploding like that. Yeah, I don't know what to do about that. Yeah, I'm really not sure how that, why that happens. That's just weird. It's just strange. Interesting. Yeah, I'm not... I mean, I guess I'll do it again and see. You know, is it a speed thing? Right, some kind of like weird timescale thing happening. And it's gone. Okay. Yeah, I don't know what that's about. I mean, honestly, I should probably just have like a totally different collider for interacting with dynamic objects. This one is for non-dynamic objects. I should probably just have like a full body one. So I'm not crushing a thing, which is essentially what this is doing. I'm crushing it. It wasn't happening with the smaller time steps, but I guess 1/60 is just unacceptable for it. Whatever. That's not a concern right now. I don't think I'm gonna have... I probably will, but that can be fixed later. That can be fixed by just like having a hard limit on its velocity. So if it ever tells me its velocity is something insane, I just say nope. Nope. You're limiting to like 5 meters per second or something, and no faster. Or probably just like doing my own air resistance would probably really save that, because it would instantly have like huge velocity and it'd be like a lot of air resistance applies. And it's a light object, so the air resistance would be pretty powerful. So I'm going to disable counteract gravity, possibly depending on grounded legs. Man, I'm so tired. Before I can really get into it, I do have to create a skeleton, which means I have to get Blender open and have some like basic model, which is gonna be handled here. I'll just make 2 models, I guess, so I can test the 6 and the 4 leg all at the same time. Probably just have them go over like a course, like they'll just walk in a straight line, and there'll be obstacles in their way, uneven terrain, slopes, walls, things like that. Do like a 20-degree like triangle or something from there to walk into to go like, you know, pretty much backwards as a forward vector. Yeah, getting a pathing to work like that. I mean, technically, it should be possible to create a nav mesh that's like that. That's not just like a 2D plane. And it could path find. It could say, yeah, like this like weird shape here is ground that you can stand on. Because my thought is, you know, the player's up here and there's a wall facing like this. The creature wants to go this way. This vector is like perfectly counter to its plane. So then it says, all right, well, you know, how to, I don't know. I shouldn't even be thinking about that. That's really not part of this. It just needs to be able to handle a desired direction vector and act appropriately. Oh yeah, this needs to incorporate legs, leg movement for turning, so that travel don't travel through each other. Yeah, incorporate leg movement for turning. I mean, honestly, actually, I didn't even realize this, but I do have this method, calculate ground forces. This is kind of my in. It's kind of my in. It'd have to be reworked so that this shapecast doesn't even happen there. We do ground forces, and then that's what determines if we are on the ground or not. I mean, that would, yeah, this should, probably all of this should move into just a calculate ground forces call. So I probably do handle input. Maybe I even have an error call. So I say, this can literally be anywhere. I just have it up here for kind of no reason, but it can be anywhere. But all the code around calculate ground forces could just be put into calculate ground forces. So then I could override that for the spider, and that allows it to do things like, I have this spring force where I can say, all right, let's oppose gravity. So it can literally be an opposition force to gravity to stop it from dropping. And it's pretty short. It's really just calculating. There's some friction stuff, which I don't know. I could just have calculate a spring force as a function, and this I mean, yeah, this friction thing's kind of like randomly in between here. That doesn't really make much sense for its setting. Because spring is calculated here, but then it's not used until way down here. So it could just be right above that. It really could be. It does use ground normal, which doesn't change. So it could just be down here with that. Yeah, okay. So there's going to be some reorganization. Alright, so maybe I can start coming up with a plan then. So here's the plan. I think the first thing I need to do is reorganize character controller to support custom spring function implementation. Should be such that Spider can just override that method and everything else works as expected. So I guess I would need to go through here, look at precisely what parts I know the spider needs to do differently. I'm thinking slope and stuff like that probably doesn't matter, so this may need to be a toggle. It could also just be like max slope angle is 90, or it's some uncapped value, or I just have it turned off somehow so that this part is just skipped entirely for the spider is probably what should happen. Or I just have a custom check as well. This could also be its own function where, I mean, I'm giving it a shape cast. I'm definitely thinking at this point for the spider. Okay, I remember now. I'm all over the place, by the way. So scattered. This is why I tested these being inside of each other. Doesn't really work. My thought was the main body will be the rigid body, and then I'd have like a leg, which is just like a smaller sphere that I let have interaction, or like the leg part is something. I guess it would be like a physical bone simulation. So I have the joints. I have joints set up so that each bone essentially becomes a rigid body with its own shape, but they don't consider collisions with each other. I could do that. I could have a physical bone simulation. That sounds expensive though. That sounds like I start to limit really, really heavily how many of these I can really have. Because ideally, or maybe not, maybe it's not that big of a limitation, because I think I've seen Jolt physics demonstrations where they just have like character bodies or like character ragdolls falling into a big pile. They can have like literally 100 there, and they're all touching and interacting, and it's not, doesn't do anything. So that could be a thing. I could test that, but I kind of don't want to. If I can make it work where I just have a sphere for the leg, like around the contact point for the leg, that would also help prevent it from intersecting its own body, because that rigid body, they'd collide with each other. Also, it wouldn't really be a sphere, it'd be a capsule, just the same size as the last leg. It does mean that the joints between this leg segment and the body don't have any collision, which I'm totally fine with that. That is a simplification that would be nice to have. I could still use a physical bone simulation as well, because I think I can just delete the parts of the body that I don't want to simulate. So I have a skeleton that has like just that end node, which would save me time probably, or save me effort at least. We're trying to set up, we're doing my own connection between the two, where I have to say, all right, here's the sphere, let's try to put the leg there, and if we can't do that, put the leg as far as we can and then bring that sphere back or whatever. Or, all right, well, we can't get the leg over there, so we got to move the whole rest of the body and apply like some huge torque or whatever. That would solve that problem. If they get hit with a high enough impact on a leg, or I guess like the main piece of the leg that I have simulation on for. I can even, I mean, that's probably the right way to go. Probably use the physical bone simulation, start with just the ends of the legs having collision. Maybe I leave those other colliders there, but I make sure they're disabled. And then I can just turn them on later for performance tests and see if it's suitable, see if it works. If I do that, I want to look at this. There was something around here. Here it is. I was thinking this is like incredibly expensive. I mean, it is really expensive if you have a body with a lot of bones, but maybe it's not. Maybe it's not so bad. I'm going to copy this video URL and I will save that too. Reactive bone simulation. Yeah, this is 6 minutes. I'm gonna go and watch this through.
To get characters to interact naturally with the game environment without having to add a bunch of extra animations. In this video, I'm going to cover how I was able to get an active ragdoll implemented in Godot 4.0 that could also play traditional animations imported from Blender. First, we need a rigged model with animations. Here I'm reusing the rig I set up for the Leviathan Axe video. It's essentially a Mixamo Y-bot with some animations that I merged together in Blender. We're going to need two of these. One will be the active ragdoll, and the second will play the animations that we want to copy. Give them names to help differentiate them.
Yeah, this is
Here,
why I
I'm
thought it was
just making them
bad
both local
immediately,
to the
because
scene,
you have
just so
two
I can
bones.
edit them in the
You have
main
two
scene
bones
to
running
make
at
the
the
video a
same
little
time.
easier to record.
I mean,
Set
in
an
my case, I'm not really gonna have. I mean, here's the problem. I would love to have animation. That would be so nice to be able to animate these creatures. These robots to do anything besides just static walking towards you and literally being totally idle, doing absolutely nothing otherwise. Right?
Animation to play
So,
on
yeah,
the
I'm just gonna watch
Animated
this and
animation
see
player. Now let's set up our ragdoll. Click
what
the
they
Physics
do.
Rig Skeleton 3D node, then in the toolbar at the top, click the Skeleton 3D button and click Create Physical Skeleton. This will create our physics bones for us. Now clean up the generated bones. If you have a simple rig, this will be way easier, but if you have a complicated one, like I have from Mixamo, you'll need to spend some time tweaking the bone collisions and removing bones that aren't needed, like the IK pole bones. Once you're happy with your bones, select them all and set the joint type to generic 6 degrees of field joint. This will give us the most control over our joints. Attach a script to the skeleton and add this line of code to start the ragdoll simulation when the game runs. Try running now and see how the ragdoll looks. If it behaves strangely, then you need to keep tweaking the bone collider sizes and joint parameters. You can alter the joints' X, Y and Z limits per bone to allow for a more natural range of motion. Once you're happy, it's time to start working on getting the ragdoll animated.
Hold on. So ass. I bet you find it better with IK. Well, sorry. I am going to be using IK for the legs, but at the same time, I would still like to have animation, be able to animate. So it's like trying to figure out how. I'm looking at a solution to see if I can fit that into IK. You can if you're using the new Godot. What do you mean exactly? Explain. I know at the very least the legs. I've thought about it. Animating them would be nice because I can do stuff that I can't really do with code. Or at least it would be in the case where if I want something to look different, I have to go to code to change it. New Godot. Well, yeah, I mean, I'm okay. So here's what they have. Okay. Also, I said explain and you just repeated your message. So their skeleton IK, they say don't use this. I saw in here IK modifier 3D, which I'm assuming is what is the new thing to use. And this is what I saw. Jacobian fabric, whatever that one stands for. Maybe this one would be cyclic coordinate descent. I mean, I don't know. Maybe this would be better. But it looks like from these are all exactly the same. They don't have any custom settings. You just pick one and you can swap it out. So I have to do this for testing, like performance, to see if how many can I get going at once. Like, does using this one, is this probably the worst one to use? No, they are different. The one that I'm looking at right now, the IK modifier 3D, or is there something else? You keep saying they're different. What is it? Stop telling me there's something different. Tell me what it is. I'm getting a little bit annoyed. All right. I hate, don't do that, Firefox. Quit making groups.
Six updates.
It's literally what it's literally what's on screen right now. It's literally what I'm looking at. It's literally, yeah, this. I know they're all different. They have different things where they say, oh, you should use this for this, use it for this. Like I said, it looks like you can, okay, let me prove what I'm trying to say here, by the way. Maybe you don't understand. This, iterate IK3D. There's nothing in here that says Jacobian IK3D. So whatever I set up for any of this on this one, I can set up exactly the same way here. And the only difference is the way that it looks and the way that it looks in motion. So what I'm saying is, for performance or for looks, I can optimize for that. I can just swap them out. I don't have to. There's not a different setup. It's just the exact same thing. Then what do you want? I don't know. I'm just saying, what I was trying to say is that, yes, you said there's new IK, and I said, yes, here it is. This is what I saw. And then I said, it looks like I can swap them out to see which one I want. Because they are different. Because I know they're different. Otherwise, they wouldn't be 3 different things. Of course, they're different. But their setup is identical. There's nothing different than any of the settings between any of these. They're all the same. That's what I was saying. So I'm aware of this. But that's really new. This is an existing thing, and I'm looking at this to see...
To get our ragdoll to attempt to...
Because otherwise, the thing is, IK isn't some kind of... It's not like this is actually any different from this. This is just the new way that they do it. So it used to just be skeleton IK 3D, and this is what you got. You couldn't pick how it worked. There's a magnet thing, which is different. But now you can pick from 3 different ones. And it seems like it's made to be that I could implement, if I wanted my own IK, I could extend iterate IK3 and probably implement whatever method I need to implement. Probably. Okay, it doesn't look like it. It looks like you can't, it looks like you don't implement anything. Never mind. But I guess the idea is there.
Match the animation playing from our reference rig, first we're going to have to find the difference in position and rotation of each physics bone, and then
I'm just looking to
animate
see
rig
like
path.
what he's
And
doing
secondly,
here.
apply physics forces to
If
move
I
them
can
into
apply the
correct
same
position.
thing, I mean, I should be able
I
to
was
because it's
originally
just
planning on
IK.
using the generic 6 degrees of field joints spring constraints to achieve the latter part for us. But after trying and failing to get these values to actually do anything for a while, I dived into the engine code to see what was going on and found out they just weren't implemented in 4.0 yet. Oh well, we can achieve this ourselves pretty easily using Hooke's law and the physics.
I wonder if that's implemented yet. I'm actually curious about that. What is that? Joints. I'm already lost. Servers. What's a physics server thing? So that'd be like Jolt does that. Whoops. I'm curious. Server. What? Wait, what? I'm lost again. Physics 3D joints. Server. Physics 3D. They're gone, I guess. I scrolled past it. Jolt. Never mind. Looking at modules, Jolt, joints, 6DOF. Do they do anything? I guess they do. Do they do anything? I don't even know. I don't even know. Still don't know. Alright.
Physics bones linear and angular velocity properties. Hooke's law is very simple. We can calculate our spring force by multiplying a stiffness value by the displacement of the spring. Displacement in our case means difference between our current and target positions. This alone will make a spring that moves back and forth forever. We can apply some damping by subtracting a damping value multiplied by our current velocity from the previously calculated spring force. Put this Hooke's law function into the script we created earlier and export some stiffness and damping variables. Create a set for both linear and angular movement. While here, let's also export a variable for our target animated skeleton. To help see what's going on, I'm moving the animated rig to be a child of the physics rig, and move them to overlap. I'm then setting the animated rig to be slightly transparent for a ghosting effect. Back in the script, create a variable to hold all of our physics bones. In the ready function, get all children of type physics bone 3D and put them into the physics bones variable. Then, in the physics process function, loop over our physics bones. We can get the animated bone and physics bone's current pose information by calling the getBoneGlobalPose function. Even though the function has the name global in it, the transforms that gets returned aren't actually global, it's relative to the skeleton the bone is from. Physics simulations tend to run in global space though, so we can easily make the transformation global by multiplying the skeleton's global transform with the pose data. Okay, let's handle the linear forces first. To calculate the displacement needed for Hooke's law, take the target transform position and subtract the current transform position from it. We can now just pass all our data into the Hooke's law function to calculate our force. Then we can just add it to the bone's linear velocity value. That's it. Now let's sort out the rotation. We can calculate the rotation difference by multiplying the target pose's basis with the inverse of our current pose's basis. We can then use the getEuler function to get this value in vector-free format. Then pass all the data into the Huck's law function just like we did before and apply the resulting force, or torque in this case, to the bone's angular velocity. And that's all it takes. Just like the bones themselves, it can take a lot of tweaking to get the spring values feeling nice, and it really depends on how realistic or cartoony you want it to feel. I found that these values worked well for me. If you want to add an even further level of control, we can hide the physics rigs mesh too, and add a third rig that will interpolate between the animated and physics rigs poses. Attach a script to this new interpolated rig skeleton. This script is very similar to the physics skeleton script, except we iterate over every bone in our skeleton, and we use the set bone global pose override function. As we mentioned before, poses are relative to their skeleton, not the world. We can use the global transform.affine inverse function to achieve this. This should give you a good base to build on for your own implementations. There's some further ways you could improve this, like a way to stop the physics bones from getting trapped in the world geometry. I'm really interested in hearing your ideas. Please put any suggestions you have on how you'd improve this system in the comments below. I think that about does it for this video. I hope you found this useful. A GitHub project with the code you've seen here will be
But I could keep looking at stuff. What is this? Also, wait, is this the video that you sent me? That's funny. So the video you sent me is literally recommended right here. At the top. I'm watching this next.
We finally have a proper IK. Hey, it's Lucky.
Very loud.
With the release of Godot 4.6, we finally have a proper IK system within the engine. Today I'm going to be teaching you how to utilize the new IK features within Godot and give you a bunch of real-world examples of how they are used in games. From giant science fiction robots to medieval fighting simulators, the application of inverse kinematics is truly endless.
Get that boy a duvet! Tuck that boy in, alright?
First off, let's answer the question, what is inverse kinematics, or IK for short? IK is a mathematical process of calculating the rotation and position of a bunch of bones in a spine.
Right,
for example, here we have 5 joints connected all together with a starting location and a target the end bone needs to reach. If we move this target around, you can see all the rotations and positions of the joints are calculated to reach this endpoint. In the Godot 4.6 update, we are giving 3 different types of algorithms to achieve the same effect, but you can see they all achieve it in quite a different way. One important characteristic to take note of in IK is whether they're deterministic or not, meaning whether the last location of the bones matters in the next location. Within all these IK nodes, we'll take the Fabric 3D one for example, you can see a checkbox for deterministics. If we enable this, the position will always be the same with the same given target and starting position. So now every time we move to the same target, the rotations will be exactly the same. And when we disable deterministic, the starting position and the target might be at the same position, but the solution might be different based on the last position it was in. Whether you want your IK system to be deterministic or not is really dependent on the application. If the position of the arm matters for gameplay purposes, you probably want it to be deterministic, so you get the same results every time. But if you're just going for a visual flair or something more organic,
yeah, mine,
you might want to have it.
I guess mine would have to be
so you get more
deterministic.
natural and smooth movements. Each of the different algorithms given to us in Godot 4.6 have their own advantages and disadvantages. And within the documentation and even in the create mode,
okay, here's deterministic, right? It's probably not a good word for what they're actually doing. It's probably better to say just reset before transform. That doesn't really mean deterministic. Because I can say turn off deterministic, but I still have a deterministic simulation. As in, the robot wants to go this way, so it turns and goes forward. That whole process of decision and the motion can be deterministic, which also means the final orientation of the legs will be deterministic as well. Even if I have it be not deterministic according to IK. So I think I would have that turned off unless I'm having problems, and then I guess I would have to turn it on at that point. And I'm sure there's an optimization benefit to using deterministic, or performance benefit to using deterministic, or probably not, because it might even be slower to not use determinate or to use deterministic because it has to keep resetting the transforms every time instead of just using the existing transform
menu. You can find the
so honestly, if they, depending on how they implemented it, deterministic should be slower
recommended use cases
because it has to
limitations of
reapply
each of
the rest post every
Besides the
bone
chain
before it
IK
can do anything.
systems allowing for more than 2 bones in a chain to be solved, we also have the 2-bone IK system. This is the one you'll find most used in video games, as most IK applications are only consistent of 2 bones. when we're talking about hands or legs, for example, we only have the upper leg and the lower leg, or the upper arm and the lower arm. And this is what's most used within video games and what we'll be using the most within this demo. Now let me quickly run through setting up a chain IK system like this. You can find this project in the description, or if you have your own armatures, you can use those, of course. But for this demo, I'm going to use my own one, using the IK arm. This is how you would import a model coming straight out of Blender or any other 3D software. I'm going to make this local so I can have access to the skeleton. This is what actually contains all the bones. And all the IK nodes need to be a child of the skeleton 3D. So we'll right click the skeleton 3D, add a child node. I'll use the fabric 3D, this is the one I found most effective. And apply it. Now we're going to need a target for the IK to solve to. On the armature, I'll add a child node. You can use whatever node that has a position, so any 3D node. But I like to use a marker 3D. It's just an empty node, but it has these little axes so I know where I'm solving to. I'll put it all the way at the top of the spine, and then go back into the fabric 3D node. Here, within the settings, we'll add a new element. Here it requires us to set a target node. So we'll select that marker 3D that we just added. Then we'll select our root bone, meaning the starting bone, which will just be bone 0, and the end bone, which will be bone 5. And now as we move the marker around, you can see it solves to the marker. If you would like some more control over your spine, you can also add secondary markers. Set a second one, then go back into the fabric 3D inverse kinematic node, and remove this original setting. We're going to be adding 2 different types of settings. Add a new element, set our target to that second marker, set our root bone to the first bone, and set our end bone halfway through the spine. This will solve the half of the spine through that first bone, and then the complete spine to that last marker. So now for the second setting, we'll add a new setting.
Ooh, okay,
select that
interesting.
first marker, that's all the way on top. Then go to the root bone, select the first bone, and the last bone. And in order for this second control marker to work, we need to be deterministic. We cannot have the last position matter because there's too much calculation. So we'll enable deterministic and up this angle limit. This means how much the bones can rotate within a single step. And because there's only one step, we need it to be all the way at 180. And now if we move that top marker and then play around with that second marker, you can see we have a lot more control over the spine. So how can we actually use this technique in gameplay?
That's how you use like a magnet.
One recent famous example is the robots from Arc Raiders. They all use inverse kinematics to solve the legs to the ground and to the body. So here you can see
I should probably look at that too. Someone told me that
and all its legs
Arc Raiders
are nicely
has
plopped onto the ground.
these
I'll show you how
things.
this is done in a second. But here
They may
if I
have
enable the
like
gizmos again, you can see all those second markers are up
some
there to keep the legs
dev
curved upwards,
video of
otherwise
it.
they might solve downwards, which would look weird. And we have our target markers on the ground. Now in this demo, I'm actually doing a little bit more trickery. I'm using the spring arm 3D nodes. These spring arms are basically raycasts that point down and set their targets to whatever they hit. This way we can always mount the feet to the ground. And if I run this demo and I move around the robot, you can see the feet will always stick to the ground because of those spring arms. And all I'm doing here is moving those targets that the IK solve through. So it's a very easy way to keep your characters grounded and make them interact with the real world in a natural way. Now let's look at my favorite application of inverse kinematics, arms and legs. In this demo, I've set up a first-person controller. And
Also, I feel like his settings were kind of wrong. I would have thought his first target would be solving from 0 to halfway, and then you would take the other half and solve from there forward to the actual target. Which if you're to use like angle limitations, then it should work then, right? Otherwise, in his case, it would just be a straight line and a clean break to another straight line. But if you have angle limitations, then it should look better.
Meaning I'm only animating
if you
the
just
stick
do
and the
part
arms
way.
just solve to the stick, leading to these natural animations. As you can see here within the player, if we grab the stick and move it around, the arms instantly follow. This is such a nice time saver for first-person animations, and even third-person animations can be done like this. In this demo project, I've also set up this full IK character, meaning every joint is controlled with inverse kinematics. You can see the arms and the legs are fully IK'd. And I wanted to showcase this super easy walking animation you can set up with IK. If you just move one marker back for one leg and the other one to the front, and you grab both, you can do this with code, of course, and you just rotate them, you get a walking animation, just because they solve like that. And even a walking backwards animation. How amazing is that? In this demo, I've also set up a look at node. This is basically an IK solver for only one joint. So here I have the look at node, and the character will always look towards this node. It's going to be really nice for third-person controllers when you want to look at enemies or interesting things in the world, or just where you're aiming. Now, one problem I'm also showcasing in this demo is solving the last rotation. What this means, if we're going to this marker,
He is
you see
learning,
we
I
move
am
the
learning.
arm around, the hand will also be solved. And no matter how we rotate this marker or move it around, the hand will always be solved into the last rotation, which is probably not what you want. If you want the character to hold an object or a weapon, you want that hand to match the weapon. For this, we have the copy transform node. This allows us to copy the transform of a node to a single bone. And here, as you can see, I've selected that hand bone. The reference type is a node, and I've selected that hand marker. So now if we move around the hand marker, you see the hand is always in the rotation of the marker. This allows it to be matched to an object it's carrying, or a weapon, or just for certain animations where the hand needs to be in a certain position, for example waving. Now while this system is impressive and allows for a lot of freedom with your characters, if you want to do animations with this, you still have to animate them manually, just like you would in Blender. So there's no real use to having the system completely control the character. And that's where this last demo comes in, the animation demo. Here we have existing animations on the character. So we just grab this walking animation from Mixamo, and then we're mixing in inverse kinematics. So the right arm here is controlled by inverse kinematics, while the player is walking. I've even set up a look at node for the spine, so her spinal bone right there is looking at this target node, allowing her to work sideways, at an angle, and even walk while looking up, allowing you to blend between animations and procedural data given to you by the game. So when you're aiming around, you can blend between the aiming position and the character position. And all these IK nodes and bone modified nodes have this parameter called influence, and this will basically say how much of the IK system to use and how much of the original animation. So you can see the right arm is now completely stuck in the air. So I can lower the influence.
Okay.
We can nicely blend in between the animation and our IK system. Now let me demonstrate how to set up a system like this real quick. It's very simple. We'll remove the arm IK and the body look at, and then we'll set them up again. Under the skeleton of the character, we'll add a child node, and we'll add a 2-bone IK system. Then, in the settings, we'll add an element, and because this is only a 2-bone IK system, we only have to set a target, which will be...
I think I've got it. But I will save this. Do I have extra spaces here? Demonstration of IK and blending with animations. I'm trying to think, like, what would they do when they're sitting there? Like, maybe they bob a little bit, but how do I mean, that's not really an animation. That's just like, that really would just be code. I have like a sine wave or something. And maybe, and that probably doesn't make sense either. They're not alive. Why would they bob, right? They are pure algorithms. So ideally, it should just be straight up coded. Anything they do should be programmed, because that's what matches. TPS. Okay. I want to look at, I'll look at that, but I want to look at wait, what? Oh, this is not the same video. This is the same guy, but not the same video. Okay, well, he just says brand new node. I don't even know what that is. This is 11 months ago. It's probably not relevant. I forgot what I was going to look up. Right, I want to look at Arc Raiders Spider Bot. I want to see what they're doing. Okay, there's that. I don't know what that is. I just want to see. Is this probably? I guess this is probably what I should watch. This is like an official like showcase of it, so it would make sense to watch this. So a giant 4-legged thing. Okay. Looks like 6 legs to me. Oh, he just started running out of time. Okay, hang on. This is really, really simple. So there's 3 segments, 3 legs. And this is kind of how I was thinking they might, I mean, no. I have to think of like what these robots are actually made for and what they're doing. This is straight up, we want an enemy, let's make the enemy. I have a unique case where this is a robot that's been essentially hacked and reprogrammed to attack you. So it could just have weapons on it. It could literally just have a weapon on it. Like, what is it trying to do? Like, I mean, it looks like in this case, its plan is to jump on you, and I guess do a little bit of damage. And if too many get on you, then you probably just die instantly or something. Well, this was actually interesting because this is one that I was actually thinking of just having. It's called Pop. I'm assuming its whole thing is that it rolls towards you and explodes. I was thinking of like having a flying thing that when it sees you, that's what it does. It just goes straight at you and blows up. All right, this is not a very good video. This does not show them at all. This is like they made the first half and then they realized they have 10 more things to show. And so they just rushed through them and had like a 1 to 1.5 second clip of everything else. It's a very awful video, actually. Oh my god, the shorts. All right, never mind. I can't look at that. All right, forget that. YouTube is cursed. All right. YouTube is overcome with the trash. Okay, I'm guessing his hands are not IK at all, though. There's probably like a look at for the, a look at with some shoulder trick, probably. So his shoulders like want to look that way or something, which orients them correctly. Okay, so I can't... Root motion. That does mean this is not... Making it a physical model would be hard. This is... I would have to use... I don't know. I was thinking maybe I want to do some animations for legs, but how would that even work? It probably should just be totally procedural. Because that produces a certain look that a robot would have. They're not animated. For like an actual character, for the player character, still not fine because I have a physical, I have a rigid body. Trying to like what will I do for because my My thought for the bipedal robots that you'll encounter, which are essentially just meant to be human-shaped robots that can use tools made for humans. Essentially just two legs that go straight up into like a beam, and then that's like the arms, right? So they'd be really light, ideal for combat because there's no center mass to shoot. There's just a gap. Because why would you create a whole torso piece if all you need is just a motor? It's just legs. You just need motorized legs, right? I guess the real question there is like, where would you put a computer in that? I don't know, maybe it'd be on like the back side of that. Like maybe the beam is like a short little box around shoulder height. And then you would have like a visual case just to like model a human body that sits on top of it. So it's not like creepy looking to walk past it. But it would just be totally facade. Like it could have a head, but the head's completely facade. There's nothing in there. It's just empty. The real cameras are probably just attached to the shoulders or something. A good, like if I'm thinking about building a military type robot, I want to have the smallest front surface area possible. With the restriction that it has to have two legs and two arms. So it can traverse human-made environments. It can use human-made tools or tools for people. I guess the concern is that, you need a power source, you need a computer on that somewhere. But then I guess my thought is, what are the most vulnerable pieces of the body? Probably the most vulnerable piece is the connection between the arms and the legs. So you would armor that up. And you would put all your delicates in there too, because that's going to be the part that they probably want to target anyway. So put your delicate stuff where it's already delicate, probably would make sense to me. I wouldn't say to have, all right, this is power's delicate, and now we're going to invent some, like, we're going to put the computers on the knees for some reason. So now the knees are really important to maintain and protect. Anyway, back to this. I just want to ramble for a minute. Weapon copy transform modifier. LH2 bone. Okay. Left hand. Right shoulder bone attachment. Target pivot. Okay. That's a weird way to set it up, but all right. What? Wait, what? Did you not just change the same thing twice? I'm so confused. Oh. He picked the different... Okay, they're stacked on top of each other. I see. I was like, how does he rotate the same node in the same way and it do two different things? He was rotating a different node. Right, okay. Right, I gotta take the dog out. Actually, that's what I'm gonna call it for today. Did I say this? This will be good to look at. Just resources for inspiration. Let me get a better link. Set up for third person nations and IK. Source available to look at. Okay. That's gonna be it for today. Character controller is like pretty much totally done. I do, all right. The first part of my plan, reorganize it. And then I have more stuff to do. I'll probably just write this out. I probably won't. But yeah, that's next. Still looking around, making sure I'm totally geared up. I've seen everything there is to see, and I can implement how it needs to be implemented. So yeah, thanks for watching. I'll be back tomorrow. Goodbye.